Am I audible?
Yeah, I do hear now. Okay.
Hi, Makni. Good afternoon and good morning in the UK.
Yeah, good afternoon.
I think, yeah, there was a confusion between morning and afternoon because of the time difference.
Yeah, I put it in my calendar without thinking it's 2 o'clock. Okay,
No, it's
yeah,
okay.
sorry for the delay. Yeah. Okay, supposed to start at...
No problem, no problem. Yeah, we were supposed to start at half an hour, means half an hour earlier, but it's okay, no problem. So we'll we'll manage. So you can also means it was 90 minutes, so you can cut down a little bit depending on
Yeah, it won't take more than an hour. Okay.
yeah. So anyway, so I'll just give a brief introduction about the participants. So the participants are mostly faculties and research scholars from all over the country, and they're from either computer science or electronics and communications. And some of the participants are also from mechanical, civil, and other departments. And participants, so now let me introduce to you today's speaker, the first speaker of today's first session. So Professor Mathini Selathurai, she is a IEEE fellow and she is the professor of signal processing and wireless communications and dean of science and engineering at Heriot-Watt University in Edinburgh. She has over 20 years of research experience. She is internationally recognized for her work in wireless communications and signal processing. And she has held visiting roles at Bell Labs, USA, and the Canadian Communication Research Center, and has published over 250 peer-reviewed research papers and 2 monographs. So her research spans in various domains, primarily in machine learning and statistical signal processing for 6G wireless systems and applications. She has won several awards in her career, and some of them include the IEEE ComSoc WIA Mentorship Award in 2022, then the Fred W. Ellsberg Best Paper Award, and the NSERC Doctoral Award. She has served as an editor for IEEE Transaction on Signal Processing. She has chaired IEEE SPOC 2016 and contributed to the IEEE ECOM Technical Committee. She currently serves on the IEEE History Committee, the UK Research Council Strategy Advisory Team, and is a fellow of the Asia Pacific AI Association and the Women's Engineering Society of the UK. So with that, I hand over the mic to you, Professor Selathurai. So you can take over now.
Okay, so good afternoon, everyone. Sorry for the delay, but I actually was traveling from US yesterday, so I kind of forgotten to check yesterday, so my calendar didn't show up as the morning event. So apologies again. So I have done some work on using AI for telecommunications and wireless mainly, and some optical networks as well. So I'll just share some of the work we did in a brief way, like rather than going in deep. Do you see my screen? So I think I got it.
Yes, your screen is visible. Yes.
Okay. Now it's in full screen mode. Okay. So it's a bit of like, I started my PhD like 1998. Even at that time, I worked with Simon Heikin. So I guess some of you might know Simon Heikin. He wrote a number of books, including neural network books. And he was very enthusiastic, and he said that we should try neural network. The neural network is the old name. Now it's just deep learning. So you have number of layers, and it goes deeper and deeper, and it's pretend to be a human brain kind of stuff. So the problem given to me was, whether we can apply neural network for communication networks or communication transceivers and so on. But I did work on physical layer. I didn't work in the network layer. So it's just about the physical layer, whether we can improve the physical layer using neural networks or machine learning. I mean, signal processing, it's more like a human brain. It's very different from human brain, but it's just like a simplified models of how we can actually process signal to remove noise. Basically, removing interference and noise is the main problem that we face at the physical layer. So yeah, all the signal processing work very well for telecommunications. I mean, till now, there's very few places that machine learning is used in telecommunications, but it still works, but we want to go further. So yeah, at that time, 1998, when I started, I did a few papers on using neural network. Like at that time, it's more machine learning, at support vector machine that I used mainly to design transceivers and so on. So it was interesting, but it wasn't like outperforming the traditional or conventional signal processing techniques in a complex environment. So there's even when we go to machine learning, there's 2 kinds of machine learning. So some of the machine learning are designed, we need to choose which machine learning we have to use. So we will go into that now. Yeah, so it is like almost 25 years, more than 25 years. I've been looking into neural network, but I haven't looked into deep until recently because now we have um, more or less a lot more opportunities, and we have the 6G. Upcoming 6G would be requiring much more intelligent techniques and so on. So there's a lot more interest now than at that time. So we will look into that and how I'm approaching, but there are so many people doing it. I mean, you should look into the wider literature if you plan to work on this, and decide what you want to do as well. But I will share my experience today. So, why deep learning based physical AI communication system? It's still a question, okay, whether we need. I mean, there are certain places like coding. I think it's now well proven that if we can be able to design a coding techniques using neural network, it will outperform the conventional one because then the deep learning has a lot more power, um, computational power and searching power compared to conventional techniques. But there is complexity associated with that, so there is a lot more work to do in that direction as well. So it's still a question. There are a number of challenges and opportunities in designing deep learning-based physical AI communication. In particular, designing communication blocks, um, and tackling hardware impairments for wireless network. So the neural network, if we design deep learning-based techniques, so we can actually include hardware impairments and also include a way to predict hardware impairments compared to conventional network. I mean, this could be applicable in many different places, including designing vehicles and so on. So if we extensively make a system intelligent, it may be able to predict any hardware impairments ahead of we using it. Okay, so there's a conventional system that doesn't include that. So this can be applied to mechanical engineering or healthcare, devices and so on that can prevent many different disasters if we extensively use deep learning within any system. So this all, I mean, none of them are proved, but these are like, the expectations basically. Another thing is the multi-user communication. So at current systems, typically any time frequency space also we can include now because we use beamforming, a lot of spatial processing going on already. So in the past, it could be we don't put more than one user in any time frequency resource. So that means any frequency and time, we put only one user. But now we use spatial processing a lot. So any time frequency space. So if we have a beam going in a certain frequency and a certain time, we only serve one user. We don't serve more than one user. So that's kind of limit the number of users that we can serve at a time. So the expectation is if we design proper deep learning techniques, we also worked on that and we were able to show that we can put more than one user. We can put two users. We can design codes for 2 users, 3 users, 4 users, and so on, to be able to communicate in the same time frequency space block. This is based on extensive search of the coding. So if you know already spare packing, so the Shannon capacity, usually we had to code it properly. When we were coding, we do a spare packing sort of we put the code such a way that they fill up spare without interfering each other. So if you can do for multiple users for that kind of spare packing, which can be done by deep learning, it's very difficult to do by theory or hand design, man-made codes. Okay, it's very difficult to do man-made codes in that domain. So this will be very useful. Another problem is designing codes for optical fiber networks. The optical fiber is a very well-known problem. It's a nonlinearity. It's much more steady channel compared to wireless channel. But then at the ends, there is a big nonlinearity. So overcoming that nonlinearity has been a challenge. People have worked on various nonlinear Volterra filters and so on over the years. But I think we recently designed some codes, that can tackle this nonlinearity and can increase the power efficiency. Effectively, when you increase power efficiency, it will increase the distance that we can transmit. For optical fiber, the distance is critical because you put the cable under the sea and so on, so it can travel further and further. It will be very useful. It's not only power efficiency; it's also equipment-based efficiency. Otherwise, we had to put repeaters and so on. So we can do that, and there is so much future networks in various different ways, like cell coverage and millimeter waves and terahertz frequencies are rising. Like they face different challenges. So there's so many, the future generation, and also the vertical. There's a lot of intelligent vertical now. We use Wi-Fi for situational awareness in a room, and also robotics, communications, positioning, network planning, and various other places that these deep learning techniques may be useful. And as researchers and academic researchers, it's very important to work on and see the potential of the neural network. At the same time, some other people might be interested in working in how to reduce the complexity, how to bring very simple deep learning which can achieve the same performance as the deep learning that we have currently using, and so on. So there's a lot of areas that as academics can look into. And there are many other open issues in designing physical AI communication. One other thing is online learning. So particularly for wireless physical AI, the channel changes a lot. So it's very difficult to learn, pre-learn a system. Okay, like many other places, like if you want to detect cancer, for example, using deep learning, you can collect a lot of samples and you can train. I mean, you can continuously train, but it's much more reliable in different places because they don't change like wireless channel. The wireless channel changes a lot. So there is a need for online learning. Okay. So another thing is the feedback. Feedback is very critical in communication, whether we realize or not. There's a lot of feedback going on in telecommunication to function. So, to request lost packet or channel feedbacks and various other things, how we can actually use this one within the learning. And there is a latency issue. Particularly the 5G, 6G is expected to have really, really low latency, and they have applications that require extra sensitive applications are also planned to be used within the networks. So the latency, reducing the latency. And the other thing is the buffer. We cannot hold too much data in the buffers most of the time. So there's there are different constraints coming in designing a physical AI communication system. Then if you want to use deep learning for this, we need to be able to redesign deep learning sometimes. So that's probably another interesting problem for people working in signal processing. So there are a number of solutions in the literature now. One is like deep learning, the other one is the model-based learning. So the reasons for going into model-based learning is particularly we have designed a lot of models. So the communication system functioning based on a lot of knowledge that gained with experience, and also for theory and empirically designed models and so on. There's so much of models already have been designed. They work perfectly all right for the current system. The thing is, we don't want to just throw them and then bring a new deep learning model, but rather whether we can actually do the model-based learning. So that's one of the potential question. Would that be a potential solution? This is also had to be verified. So another challenge is sometimes we need to have large-scale experiments, data collections, and also another thing is privacy is an issue. They say that when you have collected a lot of data, and sometimes we can't exchange data for different places, so there's something called federated learning. And the other thing is, if you have learned for one problem, whether we can actually transfer that learning to another problem on the way, and so on. There is a number of questions to be answered in this domain. Okay, so we will be looking into some of the work we did under these domains, and we will discuss this now. Okay, why deep learning? Now, okay, why it wasn't before? And as I said, I started 25 years ago, but I wasn't able to do much at the time. The main reason now is unprecedented advances in deep learning. The deep learning has started growing recently, so there's an interest to use that in wireless as well, because wireless is one of the top technologies now, and everybody using it. I mean, you know, it's almost important as any other technologies now. You know. So the deep learning is available. Deep learning is developing. So why not we use as well? And the other thing is advances in computational power. So there's another technology, you know, within the past 25 years, a huge development in the computational power. And the other thing is data is the new oil. I mean, there's a huge amount of data available already. Still people talking about data centers. And so these three things now coming together, it's helping us working on deep learning more into that. So another motivation is the expectations of 5G. I mean, although we are in the 5G, I don't think we have achieved everything. So we're going to 6G, but probably be addressing what we haven't achieved within the 6G as well. So decrease latency, we need to decrease latency. The density, like number of users and number of Internet of Things is another thing, because it's not only people, the things are also using. So there's huge amount of devices and people using the technology, so we need to put more and more users. As I said, that multi-user communication can be improved using deep learning. The latency aspect is still it's a challenging aspect for machine learning as well, because machine learning takes its own time as well. But it is a future challenge. And also higher data rates. These can be possible because we can be able to design better physical layer network. And the network, definitely network efficiency can be improved because AI can predict better paths and so on for traffic flow and so on. So the network efficiency can be improved. So there's a lot of motivation in the current system and the future systems. Okay. So now those are motivation. When I come to the traditional digital communications, you know, what's the difference we're going to make? There are two kinds of traditional way. One is called model-based communication. This is what most of academics, like, you know, researchers, and even industry is looking into. That basically model-based is just like optimization. How we can optimize, like, for example, minimize the power used, subject to certain constraints. Okay. And we try to get optimal solution based on that. But in order to do this model-based communication, we make a lot of assumptions when we formulate the problem. Okay, so when we formulate this particular problem, we would be making various assumptions to do that. Okay, so typically these are convex problems are solvable, non-convex problem, then we need to make a lot of assumptions and derivation to make it as a solvable problem and so on. So, but once we formulate this problem that can be solved, then we can get optimal solution. But these are high complexity, it takes a lot of time to solve as well. And there are some packages that we can use, but it's still high complex from the point of view of implementation. So usually they are not implemented directly into the telecommunication system. What happens is the intuition of this is taken into, and then it becomes a protocol-based communication system. So you learn something by doing model-based communication system, and then you take this intuition, and then you draw a way of protocol-based communication system. So this is what you would see in the standards. If we go and look into some 3GPP standards, you will see how the coding is done, how the modulation is done, and how all the communication system done is fully described. Okay. So to anybody be able to understand what the base station is doing and how they can implement the receivers for that. Okay, so these model-based communication systems are usually implemented as a protocol-based system. So what's the difference the learning-based system going to make is learning-based system is kind of replacing this model-based by a neural network, a steep learning network. They're hoping to be getting optimal solution in nonlinear systems as well. We don't use assumption usually, like at least reduce amount of assumptions. The expectations are they can be highly versatile. Okay, it's much more easier to bring it as a protocol-based system without losing the optimality, basically, when we do this kind of system. And it can be highly accurate. The results can be highly accurate because we don't take a lot of assumption. We can actually take nonlinear system and plug in and just use it. The expectation is low latency, given the network, the deep network is not too big. And it's also expected it's going to be low power. Okay, so it's usually some of the optimal solution that we come up with model-based can be really, really complex. And this learning-based system can be quick. Okay, in the sense, low latency comes from parallelizing. We can actually parallelize. We can have reduce the depth and have more nodes in parallel. So parallel processing can be applied here much more easily. Okay, so the parallel processing had been a topic for a long time, and model-based communication system has to be more or less redesigned to use parallel communication, but in the learning-based system, we can use parallel communications. So these are the, like, it's none of them approved, okay? It's just, none of them are rigorously proved using mathematics or anything, but it's more like an observation or experience that people claim they are versatile, accurate, and low latency based and low power based, okay? And the machine learning overall, or neural network overall, or artificial intelligence, well, we can put it like we can be divided into two things. One is machine learning and deep learning. So my title today is machine learning. We used a lot of machine learning as well, some deep learning as well, so I'm going to share both. So there's a slight difference between the machine learning and deep learning. The deep learning is usually, it's a simplest example rather than going into communication. So for example, if you want to find a machine to recognize cars, so you would train with various different cars, and it would say, like, if you feed an object to the input, it will say whether it's a car or not a car. Okay, you can input buses and vans and stuff like that, and it should say it's not a car. Okay, so the machine learning has two-step process. First step is it's usually extract features. Okay, it doesn't train the picture itself, it just extract features, and then with the features are given to a network. The deep network might be a smaller network compared to a deep learning network here, but you need to extract features, and then you train it. Deep learning is basically you don't extract features. You just give the car and train in a deep network, and it should say it's a car or not car. So there's one step reduced. So the feature extraction and the learning is done by the deep learning usually, but in the machine learning we've split into it. It's the next step to signal processing. Signal processing we will be doing, we will plan everything and we will doing every step like signal processing. But in the machine learning we would be extracting features and we'll feed the features and then let this network decide whether it's car or not car. But in the deep learning we don't even extract the features, we just show the picture and then it will be able to design it. The performance versus amount of data, the thing is, the deep learning performs better and better with data, amount of data. So if we show more and more data, the deep learning start to perform really, really well. The machine learning will perform well to a certain extent, so might exceed the performance of deep learning at very little data amount. So if you don't have a lot of data, then we should stick with the machine learning because it might perform better than deep learning. But then it will start saturating. It has a certain capacity because we decide the features. So it's depending on the features. It cannot go beyond the features. So, for example, you can argue that if I do better feature extraction, whether the machine learning would perform better. Yeah, it will perform better, but it's up to the person who is designing. Okay. So, like, deep learning is more like a human brain. Like, we also probably extract some sort of features, but we don't think about features. We just, when something is presented in front of us, we just recognize this as a car, bus, train, animals, and different things. And also the advantage of deep learning is, it can be generative in the sense, for example, if you've shown a number of domestic animals, someone is grown up with seeing a certain kinds of domestic animal, and if they see a different domestic animal, at some point they will still recognize that as a domestic animal, more or less accurately. The same with wild animals. For example, a lot of people learn various wild animals in a book, and then they go to zoo first time, they can be able to recognize everything as a wild animal, so they can easily recognize. So this deep learning has the power of generativeness as well, so compared to feature-based machine learning techniques. Okay, so when and where we apply this, it's always a question. So in the physical layer, so we have a slide more representation of model-based, so machine learning-based communications and deep learning-based communication system. So we will feed the signals in communication system, okay? And what happen is we would, in the machine learning base, we will probably extract feature extraction, say for example, how modulations and fingerprint or carrier. So these things we will extract as features before we feeding into a neural network to recognize various things. Okay, so it's different. But in a deep learning, we will just feed the communication signal directly into this deep learning system, and then it should be able to recognize all three of them. So this is basically the challenge. Okay, so it's less work for us, and it's not limited. I mean, we let it learn, like it's more like a free learning, the deep learning. We can increase the notch, increase the layers to see where they can perform, and not most of the time we don't know how it learns, okay, but it is shown to perform better than machine learning when we have sufficient data for it to learn. Okay, so first we're looking at using deep learning. So one of the work we did, actually we were not the first one to do, it was done by Tim Osher, I can't remember the second name, so I think it will come at some point, I'll show you. So he is with the Deep AI, I think. So he's the one first designed an AI-based optimal communication system. So the conventional system, what we do is we take input bits, okay? In a conventional system, we take input bits, and people who have gone through your communication system courses or work research in communication system knows this well, that we first do a data compression. It's called source encoder. So we get usually take any, like it can be any sort of signal like speech or video or image. First it makes it as binary data. So this is what Shannon said. 1 and 0. So we make it as a 1 and 0 data. But that data might be a lot of redundant data in that. one and zeros already. Okay, so we can actually compress it to an information level. So this is basically the information theory section. So we can actually use compression like source encoder. Okay, these are the impulsive code or arithmetic code or Hofmann code, those kind of codes that we use to compress to remove the redundant data to the information level. So any set of data you have certain information. Okay, so but you have a lots of redundant data. So we remove that and made it as a compressed level. And then the compressed data will be taken into a channel encoder. So this has a slightly different purpose. What it does is, when we're transmitting through any communication system, okay, so for example, you take a mobile phone, you talk, and it is received, call may be intended to someone somewhere far away. Okay, so you're calling from India to like, China, for example, and or UK, and you talking something on the phone. Okay, so it is shaped. Your information is shaped by your phone, and it's transmitted, and it goes through various different channels and come back to the receiving end. The receiver doesn't know what you talked. Okay, so it's about a guessing problem. Okay, so you talk something, they don't know what you talked, but they should be able to hear exactly what you talked. That's the challenge solved by the communication system, and it is a probabilistic measure-based system. It's a guessing game. They guess whether every bit they received is 1 or 0. Okay, so if they have guessed it very correctly, then they will be hearing what you're talking. Okay, so this is just a bit of a guessing game. It's a probabilistic measure, complete probabilistic measure. In order to make this guessing game correct, we need to be able to shape the signal properly, and there is errors made on the way. Okay, so sometimes you send 1, it will be received as a 0 because of the channels and all sort of distortion that we face along the way, and also the distortion created by the transmitter receiver, including every place that is touched, like base stations and optical fiber. Every one of these medium will make some sort of errors. So ultimately, you will receive a certain number of errors, and if we don't correct those errors, we won't be able to get the guessing game right. Okay, so in order to help the guessing game right, they have a channel encoder in between. So the channel encoder's idea is it introduce some redundancy. Okay, so the source encoder remove all sort of redundancy in the data, but the channel encoder introduce some calculated redundancy. Okay, so that can be useful to correct errors. So it's basically in different optimization way, it's maximizing the humming distance. That's the optimization performance here. Okay. Here, when you do the source encoder, the optimization is done based on, without introducing any distortion, we have to do that redundancy removal here. But here we would introduce redundancy to maximize the humming distance. So between 2 code words, the distance will be maximized. So each of the code words will be recognized properly. And then we do the modulation. So after that, we modulate in the IQ and in a different ways to maximize the equivalent distance. So it's 2 humming distance. It's like the number of 1s and 0s based on the humming distance is physically where the IQ falling in. Okay, so we do this thing and we transmit, and then we have in the receiving end, what we do is we reverse these operations. So we modulate it. So we usually will know what the modulation is done. So it will demodulate, and it will use a channel decoder, the additional redundancy that we introduce in a calculated way can be used to remove errors, so we can do error corrections. And then we will do data decompression, because a lot of data is compressed there. We can actually decompress the data to get the information. So this is the traditional way. Typically, this is not the optimal way of doing it, because we can actually, the challenge now, like, whether we can incorporate source encoder, channel encoder, and modulation together as a one package. Okay, so that's not the way it's done in the past. And there is other distortion that we actually kind of designed this system to perform below capacity, because we don't want to achieve the capacity most of the time to be able to receive signal without any distortions. Okay, so when you're sending in low capacity, you can actually send a lot of redundant bits to kind of remove errors and so on. So, but we can actually do it better. So these things are not done. It's a traditional communication block. So in that sense, like, it was introduced, Tim O'Shea in 2017 paper. He actually introduced a neural network. So he just took, actually we can include source coding, channel coding, modulation at the first aim of the work. It only introduced the channel encoded modulators. So it's sort of a coded modulation. In conventional way also we have coded modulation, but it's very difficult to design beyond a certain level because it's a little bit more work for humans. But machine learning, using the computational power, we can use a sort of AI neural network sort of encoder to do channel encoder modulation together, and then we can actually have reverse that undo. And then usually they are trained together, like, when you even design these things, these knowledges are passed here and these knowledges are passed here, like not very frequently, but it's when they are designing, and also occasionally they pass in feedbacks. So here also we have a feedback which can be used to train these two networks. Once we train, the idea is it can perform better than the conventional networks. So it is proven that these kind of designs can do better than conventional networks. So it's a deep learning based transceiver. So it was, and eventually, including us, a number of people can include source encoder as well within this system, and it showed that these networks perform better. So I have an example here that we have done. So basically this neural network is called autoencoder. Some of you working in neural network knows this. This autoencoder is sort of an encoder that can actually take an image and then it's compressed to some sort of feature level, and then it's decompressed at the output. Okay. So it is used in different places, and it can also be used in communication system design. So based on this intuition of design encoded modulation, we have also designed some system, and we showed that they perform really well under hardware impairments. The reason is, if there are hardware impairments, the conventional system doesn't take into, they don't take this hardware impairment when they are designed. But neural network, when we are learning, we can actually introduce certain level of hardware impairments and then learn it. And this learning system actually adjusts to the hardware impairment. So it performs really well in the hardware environment scenarios. Okay. So that's the nonlinear thing. Like, that's the advantage of using deep learning or even machine learning. Although machine learning has two steps, it also uses a neural network as one of the steps. So, so if there is a nonlinear aspect in the transceivers, or it's a complete communication system, if we were able to collect data and if you train a system, then the trained system will actually compensate this hardware impairment and do really well. So this is what, there's a number of papers on this from us, and there are other people who have done it as well, so you can search it. And so it's a maximum likelihood decoder. This is what we would achieve using a conventional design and maximum likelihood decoder. And this is what we will achieve. And so this is the power. This is a bit error rate. So we can achieve like 10 to the power minus 4 bit error rate at like 7 or 8 dB here. But it will take about 29 dB to achieve the same 22.1 difference. Okay, so we need 22.1 dB extra to achieve the same performance using conventional way when there is hardware impairments. Okay, and this is certain level of hardware impairments. If the hardware impairment is less and less, then we can actually we won't be able to get this much of gain. We're probably much closer to maximal activity coders. The maximal activity coders will move here. Okay, so the autoencoder based design can actually handle the hardware impairment very well. So this is one of the motivations and one of the places that we can use deep learning. So another aspect that we worked on it is the multi-user communications. Okay. So nonlinearities comes here due to interference. So if you put 2 or 3 or 4 users in one time frequency space load, they will introduce interference to each other. But in hand design one, you can use like, there is some non-orthogonal multiplexer schemes like called NOMA. And NOMA is a very popular technique that usually you have 2 users in the same time frequency space block. And then there is a interference cancellation approach that they use. And that technique was also proposed for standards, but it never been in the standards because it needs a number of information, including a successive interference cancellation at the receiver. So whoever designing receivers won't vote for that scheme because doing a successive interference cancellation itself is a challenging thing, because it can be, you need to have exact channel information to cancel the interference and so on. There is a number of, although the technique is very simple to work, but there is a number of issues in there. So not all our multiplexer schemes never work till date. So we can actually do, but in auto, like we designed some autoencoder based multi-user communication techniques. So it's basically you design the coding to pack the spare such a way that each of the users won't interfere between each other. And if there is some interference that can be learned by this machine learning very easily, because it's like interference can be a bit introducing nonlinearity. And neural networks are really good at canceling nonlinear effects. So we were able to show, compared to this is the dash curves are by non-orthogonal multiplexers. That's conventional way of doing it, as I said. People who are working in wireless communication will know what is NOMA is. And these solid curves are the ones we designed based on the autoencoders. Okay. So it's under a patent, so it's not published, but we will be soon publishing it. This. So this basically we can show that we can get like more than 3 dB gain compared to NOMA, and we can actually design it for a number of users. That can actually be very helpful in the future generation because more and more people, more and more devices are using the same frequency. So that's one of the things. And the other thing is, as a multi-user communication, it's optical fiber. So the optical fiber, as I said, has a nonlinearity. Okay. Wireless communication says wireless channel fading, which is changing all the time. But the optical network has nonlinearity, but that doesn't change that much. But it's still difficult for them to compensate. Okay. So people are trying to work on different coding for that, and but in the recent we worked with Bell Labs to come up with some autoencoder based solution here. Autoencoder based solution here, autoencoder based solution here, and it outperform the red curve. The Shannon capacity limit is in the black, it's in the red, and the these are the other curves defined by other people the recent years. Okay, PDM 16QAM is one of the curves design by Bell Labs, and we did an autoencoder that actually outperformed that. That was the closest to channel capacity. So the neural network, actually, whenever we see nonlinearities, the deep learning works really better. And some other places we can actually use it, even though without complexity. I believe that optical fiber, they will be using this because this gives them significant benefit to, and also they can afford, because it takes a lot of, data through, under the sea or something like that. They can afford to provide extra capacity or in the computational powers, but it's not possible in every wireless communication. All the receivers, that all the mobile phones, we cannot provide a neural network yet, because that will increase the cost of it, and that will be challenging for, commercialization and so on. Okay, so that's one of the application. And then the question is coding. When we were doing coding, the challenge was whether we would be able to justify this coding. This coding works really well. I mean, by experiments, by simulation, we can show that the autoencoder-based coding works really well. Then another opportunity is to, no, people won't believe if you don't give a justification for that. And typically the coding community, information theory community, is very strict on that. So unless you will be able to demonstrate it extensively on real data, okay, which is very difficult. You have to collect data from base station and so on. So this is not possible. If we do by simulation, they won't accept. Okay, so it can be, a biased result. They will claim it as a biased result. So in that case, what we had to do is we should be able to go deeper. We had to interpret the results to give them theoretical insight. So one of the insight is giving extensively analyzing the design codes and showing the equilibrium distance, harming distance, and packet density and kurtosis. So these are the measures that people are used in analyzing coding. And then we also did some design to justify that the coding that we were designing in all these cases are actually outperforming the conventional one. So that's enough basically to prove, to extend that our coding is actually matching with conventional code, but outperforming that. Okay, so the matching the measures, basically, again, equilibrium distance, harming distance, packing density, and kurtosis. So that's something that we done, and we published in these papers as well. So you should be able to see in these papers this work. So this is another work. Now, like neural network or deep learning network, if you apply it anywhere, I mean, typically, particularly in communication system or networks, you should be able to prove your coding or whatever the design that you are doing is matching the measures that typically used to identify the good codes or good signal processing. So this is one of the things that an open area that you can do as well. Okay, so those all about coding. Now I'm coming to where the machine learning is going to be. So do I have another 30 minutes or I done my 1 hour? Sudeep?
I think we still have some 10 minutes.
Okay. So quickly I go another work. Another work we did with Nokia is the digital twinning approach, in the sense like to as I said, to cell coverage planning for future networks. So in the sense like millimeter wave, very sensitive to foliage and trees and even leaves, because this is very tiny waves and it can be it cannot penetrate too far, but it's going to be affected by a lot of trees and so on the street. So the Nokia was trying 28 gigahertz to put it in the 5G, because the millimeter is one of the proposed one. They have a base station placed on the buildings, and they have a receiver moving around trees, the roads and so on. They were measuring the path loss basically to see whether the millimeter is trustable to work in urban areas. So they have a path loss model, but what we did is we did a digital twinning using machine learning. So we just get the building information and the clutter information, and then we trained using machine learning, or it's AI based and also machine learning based to train to extract features first. Okay. And using the features, we did some machine learning approaches to predict the path loss. And we were able to show that we were better than what they were able to do using the conventional way that they used. Okay. And that work also fully published here that you can see here. And basically what we have shown is for root mean square error versus path loss prediction algorithm, the algorithm proposed based on the machine learning and AI together has the lowest root mean square error compared to the other standard slope intercept is the best known fit method, and that was in the 3GPP standard based models that's here, but we were doing better than that. Okay, slightly better than that. So yeah, the machine learning could work because it's not, these millimeter waves, like it's very much depending on the buildings and the clusters. There's some very nonlinear shapes, things that they cannot be modeled into model ways. So we were using machine learning and AI together. So it's a two-step. It's sort of extracting features using AI, but then processing and using machine learning. And we were also able to interpret. Again, every time you have the interpretability is critical nowadays because people don't believe, because we cannot go extensively to do simulations or data-based methods as well. So it's easier for us to, prove with something and then do interpretation. So the interpretation is showing on the values, the weights on this path loss prediction of various different features that we use. That's log 3D of distance, clutter per street, and one-dimensional distance, log 1D distance. 1D distance means straight distance, 3D distance means the actual distance. And the street width, receiver height, clutter per link, building on both sides or one side. These are the features that we extracted as the best features based on AI, and then we use that to do a lot of different machine learning to identify things. I mean, it's very easy to go and find this paper. Yeah, so there's a number of other issues that we also tackle, the incremental learning. It's basically using some online learning, basically. Okay, there's sequential learning methods. There's online learning. There's a large number of learning that you can actually try to apply, and we tried that as well. You can find this paper here. I'll share the slides later. And the other thing is reinforcement learning is used in many different places in wireless network. So basically, it's a reward base. It's you're trying to give some actions, and then based on what action the agent performing, the environment will give some rewards. Based on the rewards, the agent will recognize what actions has to be tuned and so on. So it's just like a way of reinforcement learning, and we also use deep reinforcement learning. So there's a deep network which actually trying to recognize the rewards and plan actions for the agent. Okay, so you can use that in many different places. And the addressing latency space constraint is also challenges. There's a buffer limitation always. So that also limits the latency and space constraint. So there's a lot of work to be done in this domain. And then the question is, okay, whether data-driven deep learning frameworks a good one or model-based deep learning. So some the first few coding techniques we used data-driven fully, and the digital twinning, the path loss prediction, we used this model, conventional signal processing blocks, and then deep learning together. So there is a balance to make. So there's a lot of research to be done to identify which is the best for the task. If you're doing a PhD, you can actually take a problem and then you can compare these two and come up with solid consultancy to the industries who are actually trying to do this kind of things through a PhD thesis as well. So there are a number of work that is a good paper that I recommend for you to read here. on this as well. And yeah, so there are a lot of requirement for large scale experiments. So if we have the facility to collect data for, and for various aspects, that will be very useful as well, because you need deep learning or machine learning, we need data. So yeah, how do we collect data? There is some data and projects are available, but that's limited. So yeah, if anybody interested working on channel-based technique or equipment to measure channel sounders and stuff like that, you can actually do collect a lot of data. And some of the people, if we have limited data, whether we can use transfer learning and so on. Okay. Yeah, so there is it is an open issue that we have done further work as well. So yeah, you can find our papers by searching my name. Yeah, thank you very much. I'll stop at this point, and I'm happy to take any questions.
Participants, if you have any questions. Participants, do you have any questions? If you have any questions, you can raise your hand, or you can also unmute yourself and ask, or you can also type your questions in the live chat. Okay, so if there are no questions, then I'll take this opportunity to thank Professor Sellathurai. So it was wonderful having you. It was wonderful seeing you and talking to you after a long, long time. So thank you for accepting the invite to give us this talk. And yeah, I'll be in touch with you. There's some other formalities that that are required. So I'll be in touch with you over WhatsApp or email. Thank you so much.
Thank you very much, and thank you for inviting, and also thank you for all the participants for listening. That I hope this is somewhat useful, and feel free to drop an email. Like there are our papers. I just briefly went through everything, and I would be happy to provide codes, or if you want to continue on any of the work. Okay, thank you very much.
Great. Thank you so much.
Okay, so bye for now.
Bye, Madhani. Talk to you later. Bye.
Bye.
So participants, we now will begin with our second session of the day. So the second session of the day is going to be taken by Professor Keshav Singh from NSYSU, who gave the last session of yesterday. So I'll just briefly introduce him, as you already know by now who he is. So basically, Dr. Singh is a associate professor in the Institute of Communication Engineering, National Sun Yat-sen University in Taiwan, and he's also an adjunct professor with Memorial University, Hamilton, Canada. And he works primarily on resource allocation, optimization, and machine learning for signal processing and communications, and primarily for 6G communications. So without wasting any more time, I would like to welcome Dr. Keshav Singh, and I will hand over the mic to you.
Yeah, thank you, Dr. Biswas. Yeah, so hello everyone. So yesterday, is my slide visible? Yeah, can you see my slides?
Okay. Yes.
So yesterday we have seen the application of this optimizations in especially in the case of RIS scattered, NOMA enabled integrated sensing and batch scattered communications. In today's talk, I will go through recently 3 published papers from my PhD student, Sonia Bala. Now she is a research scientist in one of leading company in Taiwan. So she published these papers, one in IEEE transaction on communications, another in transaction on wireless communication, and third one is IEEE transaction on communication and networking. So, so yesterday I already mentioned the requirement in a 6G technology, or and also from the spectral efficiency and energy efficiency perspective. So here, just I want to summarize. So here we can see that we are expecting 158 exabytes per month. This one is in 2022, and this one is, I mean, the projected is it will go extremely, I mean, several times by 2030. Apart from this, now in 6G, we are moving through like autonomous driving and the emerging of enormous number of IoT applications. So here there are few driving forces in 6G technology. So for example, IoT, AI, blockchain, connected vehicles. And due to that, in 6G, we are expecting high bandwidth demand as well as the ultra low latency, reliable and low latency. So here, uh, here in 6G, we are expecting that we can, the integration of AI and ML with, in order to merge this physical and digital and biological, this uh, entity, it will enable some new applications. So here, so from that perspective, here we are focusing on resource optimization in RIS added, and we adopted both optimization as well as machine learning techniques. So today we mainly focus on the machine learning part. So what is RIS? So briefly, I want to go through this one. So this is a programmable surface that can control the EM wave reflected by the by alternating the electric and magnetic properties based on the by observing the environment. So here we can say that the major functionality is to adjust the phase of the incident signal in order to, you can say, optimize transmitter and receiver interactions in terms of rate maximization or power minimization with respect to, different performance matrices. So here in RIS, we use like we implement with a pin diode or varactor diodes or liquid crystals or graphene. So we are not going in detail about RIS. So we are just we are exploring the application of RIS in a wireless communication. So these are the few advantages. So this is a passive, due to passive nature of the RIS, it consumes low power. That means here it operates without RF sense, which require very low power and provide the high diversity. That is a kind of virtual high diversity in communication. Along with it extend the coverage range. Also, the maintenance cost will be very low because we can easily deploy, and also it will be much flexible in deployment. And due to low power consumptions, you can say it will improve the energy efficiency, and it will require less. The hardware will require less power. So, but issue is, let's say, a major issue is multiplicative fading, especially in case of passive RIS. So here, one solution is we can go for after passive RIS, and once we recognize that this multiplicative is a major hurdle in deploying RIS. So now we have a different flavor of RIS. One is a star RIS, active RIS. Now we have beyond diagonal RIS. So here, let's say this is one example of star RIS. So here, it covers 360. That means complete areas. So it divides into, like we have mirrors. So one part is reflection, another part is a transmission. And here it can operate in three mode. One is energy splitting mode, another is time switching, another is mode switching. So for example, here energy switching, that means energy of the incident signal should should be equal to the energy of reflected plus transmitted signal. So we must meet this requirement. Now, so let's say consider this second paper where we focus on robust and secure multi-user star RIS-aided communications. And here we implement multi-agent machine learning technique, DRL, method to optimize the resources, and later we compare with the conventional system. So this is an example. So here we have a base station having multiple antenna. It serves a multiple set of downlink users. So the subset of users, one subset of user fall in a reflected zone, another subset of user in a transmission mode. And also here we have a multiple US droppers that falls in both region, reflection and transmission. Dr. Biswas, I'm getting echoes. Hello. Dr. Ansuman, can you hear me? Hello. 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 Dr. Biswas? Hello.
எக்ஸாம் படிக்கலாம்ல எக்ஸாமுக்கு படிக்கலாம்ல
Hello. Hello.
Everyone, please mute yourself. If you have questions, please raise your hand, or otherwise, please mute your speakers. Shantan, please, Shantan or Srikant, can you please mute everyone?
Okay, now I.
Dr. Singh, you are muted. Can you please unmute yourself? Yes, it's fine now.
So in this work, we consider a kind of MISO scenario, or you can say MIMO, where the base station has multiple antenna and it serves multiple downlink user with the help of star RIS. So set of users that fall in a reflected mode, reflected part. So that is here we can say R user, and in a transmission mode that is a T user. And here remember, so the US dropper present in both regions. So here we can define different parameters along with the channels and the notations of this number of users in a reflected mode. Let's say KR, and similarly here KT, and number of US droppers. And here, since we are operating RIS in a star mode, so we have two phase shift, one for transmission and for reflection. So we can define here. So this is for transmission, this is a reflection, and where alpha T and alpha R, this denote the amplitude, this alpha T and alpha R amplitude in the reflection and transmission, along with this theta, this one is a phase shift. So we can define the transmission and reflection coefficients. So here phi t and phi r, and then now we can derive the receive signal at the kth user in a transmission mode, as well as the uh, in a transmission mode, and similarly receive signal, and this is a US dropper because we have US dropper is also present in a transmission phase as well as a reflection. So similarly, you can say in a reflection we have this 3.9. This one is a receive signal, and this is a receive signal at the US dropper. And since here we want to design the robust beamforming, or I mean active and passive beamforming. So here we consider the channel imperfections. So this is a very much practical, where the base station doesn't have the full CSI knowledge. So we can define here, let's say GK. So this is a channel. This is estimated channel with some errors. Similarly, we have for US dropper, we have this estimated plus some error. Similarly, this for users, you can say for reflected part, so HK and HE. And then here we define the channel uncertainty. We can model this one by considering worst case approach or non-bounded error. This one is defined by 3.13. So here you can say for all. So where this left-hand side of this entity, this represent the uncertainty bounds, that is upper bound of the error. So from these equations, so we can derive the SNR at the kth user, and that one is, you can say here we have this one, and so this is first part is SNR in the users fall in a transmission mode. This is users fall in a reflected mode. So remember the for the users fall in reflected mode. They receive the signal directly from the base station along with the RIS. So here we also have the direct channel, and this is via the RIS. But in the case of transmission, so there is no direct link, so only via RIS link. Similarly, we can define the SNR at the US dropper at fall in transmission and reflected. Again, we have in transmission RIS, I mean US dropper in transmission, it will have only access to RIS, so no direct channel. Here we have some direct, so we can define this one with with US or US dropper. Now, from these two equations, we can find out what is achievable accuracy rate for the kth T user. T user means kth user in a transmission mode, and this is a kth user in a reflected mode. This is a accuracy rate. Now, so here our goal is to maximize or to consider the worst case scenario. So maximize minimum total rate, accuracy rate in a transmission and a reflection mode under this channel uncertainty. So we can find this one, mean of this one, and then maximize this minimum rate under this channel uncertainty. And these are the various constants. So like first constant is what is a total power budget constant at the base station. And since star arrays operate in so this is a unit modulus constant. So we have transmission and as well as this reflected one. This is a QS constant. You can say this is a QS constant for the kth user in a transmission mode, and this is in a reflected mode. Now this problem, okay, it's not we can't solve this one directly, so we need to transform this one into convex one. Then we can use some conventional method to get the solution. So instead of going that one, and that solution will be local optima. So here one way is okay this transformation. So for example here the uh, we can transform the norm-bounded CSI error model and also the non-convex semi-indefinite inequalities into LMI's form, and then the problem will become this 3.91. Okay, so we are not going detail in this method. So this is a kind of alternate optimization and line search algorithm, and through this we can get the solution. So this is a one approach. That is a conventional approach, but we can solve same problem by using, let's say, machine learning. Here we propose multi-agent DRL framework. Okay. So here we have one agent for this, let's say, for user in a transmission, one agent for, let's say, for a reflected one, and at the base station. So here we adopt MDP approach, Markov decision process. We define. So there are three key components of MDP. We have a state, action, and reward. So we can define here. So we have the environment, and we have defined the state space, individual observations from this environment, and fit to the key this transmission zone agent, and similarly this reflected zone agent, and the corresponding R. And this will be the you can say and then there will be a joint action. Again, it will move to the next state. Again, it will go to the environment, and this process will repeat. So here we define the state space. So for example, here mainly this one is contain the information level at the base station. Okay, that one can directly obtained or through the inference. And here, for example, we have these various JK. These are the nothing but the channel set of channels. For example, this one we define theta k. This is a composite channel through this RIS. Similarly, with direct link, and this RIS. Similarly, this US dropper. So we have all these four. Okay, one for transmission, reflection, and similarly for US dropper. So we define this state, and then we define the action. So here we can say by integrating the policy, incorporating both comprehensive informing matrices. So here we have the informing matrices, that is for kth user WK, and there's phase shift matrices at the RIS and the channel error vectors. So with the help of this, we define the action space. So again, this one contain both transmission and as well as the reflected subspace, and then we define the reward. So reward will be total. So if you are considering at total t time step, so gamma t into RT. So where gamma t is binary 0 and 1. So this is a discount factor, and it represents the impact of reward at a particular time t. So this one will give the reward. So now here, this is a pseudo code of this proposed DRL framework. You can say just what we have seen. So here we are describing in a step wise. So we are doing same here as we have seen in the previous two graphs. So let's see some results on this robust beamforming design, and here we compare with the conventional method. So here if you see the first one, this one is a sum accuracy rate versus transmit power at the base station. So here we consider the last one, below one is, lowest one is no RIS, so only a direct link. So here you can say it is performing worst or giving worst performance. So reason is that because the base station can only serve the users in a reflected subspace, not the transmission. The users fall in a transmission subspace. So here the overall the performance is worst. And the second one is only direct link. Only direct link. So this one is performing um, slightly, n equal to 6 and n equal to 10. So we have, if you have a higher number of elements, so it will perform slightly better. So here, if you see the proposed one, star RIS, if we consider this one n equal to 10 and multi-agent star RIS, so this one is outperform rest of algorithms. So for example, so this one is a passive RIS. Passive RIS, that means system operates only in a passive way, and here the performance is lower than the star RIS. And similarly, also compare with, let's say, with okay, no RIS. Here again, this one is n equal to 10 with multi-agent and no RIS, only direct. So this one is of course performing better than the conventional, and but lower than the proposed one. So we can also experience the similar result in a 3.8, but here we can see on x-axis we have a number of reflecting elements. So as we increase the reflecting elements, so in case of this proposed one here with RIS, we can see we have improvement along with increasing the RIS elements, so because we are getting the diversity here. However, in case of no RIS, this will become fixed, so there will no improvement, no diversity again. So however, again here if you see with multi-agent star RIS, this one is outperforming outperforming all the algorithms. So here we can see that reason is that because this proposed one machine learning multi-agent DRL, this one is giving the optimal solution. However, the conventional method is just a local optimal. So you can see huge gap. So you can imagine if you increase, let's say, a huge number of users. If you are considering, let's say, 50 users in a reflected and transmission mode, and if you are considering, let's say, 256 RIS elements. So you can imagine the complexity of the conventional will be very, very high. However, in case of multi-agent DRL, so here if you neglect the training part, then the execution time will be very, very less compared to the conventional one, and the performance will be several times higher than the conventional. Okay, so here we have compared this one with some other algorithms. For example, with perfect DDPG, and also we have imperfect and PPO, and perfect conventional method and imperfect conventional method. Again, here you can see the lowest two curve is conventional method. So this is a solid black line. This is a imperfect case. Of course, the imperfection will dominate the system. So this one gives the worst performance. And perfect case where the base station has the full CSI knowledge or the system parameters. So here you can say it performs slightly better than the imperfect. However, if you go for another algorithm, let's say the proposed one is outperform the PPO and DDPG in both in case of perfect and imperfect. And here we can also experience same perfect and imperfect in case of DDPG and PPO. The perfect will work as a upper bound for also for PPO and DDPG. So this right hand curve is this one is a impact of QS for users. So when you increase the QS, so you can see the sum rate will improve. So because finally it will enforce each user to improve their sum rate, and then overall the system performance will become slightly better. But if you increase, then there may be fall in the total accuracy rate, because this will also increase the inter-user interference. So here, okay, we can summarize this one. We can say we have around 62.3% loss in some accuracy rate with the more US dropper as the considered parameter settings, if we have this one. But in case of star RIS, this one, it provides 27.1% higher accuracy compared to the conventional and 35.4 multi-gen DRL compared to the traditional RIS case. So here overall we can see that this multi-gen DRL, especially if we use for a robust resource optimization with imperfection or in a robust scenario, then this will outperform all the remaining schemes or methods. So moving to the next, this is another work published in IEEE transaction on wireless communications. So since in 6G now we are expecting, we want to, we can have this spectral problem. So in future, we can expect, we can find the solution with the help of integrating terrestrial and non-terrestrial network. So here we focused on both, total rate maximization, or you can say some rate maximization under a set of various constants, and we adopt a data learning approach instead of conventional method in order to solve the problem. And this federated learning, since this is a distributed, so this one is very much practical compared to the DDPG, which is you can say centralized, kind of centralized. In fact, we have also compared the simulation results. So even in that case, federated learning based approach outperform the DDPG. So here, so this is a kind of future. We can expect this kind of system model or framework in upcoming 6G or 7G, where the set of user will serve directly by the satellite or LEO or satellite, and remaining set of user will serve by the base station. So now, for example, Tesla, I think that Elon Musk, that Star, they are providing services like in Ukraine or in some war zone area. They are providing communication directly through the satellite. So here we can explain this kind of system model where some set of user can be directly served by the satellite, as well as the satellite can also monitor or detect the set of target, and it could be UAVs. So for example, in nowadays war, we can use satellite, detect the enemy's UAVs, as well as we can serve the cellular users. Similarly here we can also have the terrestrial base station, but here terrestrial base station, so this one serve the users and detecting the target and serve the users directly, as well as via the RIS. So here there will be interference because both system operate at same time, so there will be interference from satellite to the base station, and similarly here also the user will experience this interference. So there is one way, either you should have this, you can say different frequency band for terrestrial and non-terrestrial system, then both will work as an independent system. But here, let's say use the same frequency for both system models, so where in that case we can explain this interference. So here we define the satellite channel model. You can go through this. So you can. So this is LEO IJAX satellite to the IS users, so GL. So we can define this one. So these are the various parameters for this channel. Similarly, we have a radar satellite communication model. So here we have a narrowband hijack signal. So we can represent as, let's say this is a transmitted signal. So we have a total L number of users served by the satellites, and this is a precoder, or you can say beamforming weight, and this one is a for target. So because satellites serve or detect DS target. So this is a superimposed signal transmitted from the satellite. Similarly, okay, so here we have total power constants. So we have this precoder for this one as well as this satellite. So this should be less than or equal to this. So this is for satellite scenario. Okay, so rest part here you can say some parameters related to this channel modeling. We can refer here, or I mean this paper is already published. Similarly, for terrestrial networks, here you can say in downlink scenario. So this one is, let's say, receive signal. So we have a target signal as well as the echo signal. So receive signal at the satellite. Sorry, this is a receive signal at the satellite. So this is a target reflected echo signal of the interference target, and this is advice. So we have this case, and then this is a SINR of the target key S. And then here we have received signal at the LAS downlink, because satellite also serve the set of downlink users. So we have desired signal, multi SU downlink satellite user interference, interfering sensing signal plus noise, and this will be SINR. So similarly, here we have a radar terrestrial communication model. So this will be transmitted signal or superimposed signal. So here we gauge weight vector. This is a transmitted signal. There are K users served by the terrestrial base station, and this is a total, TS target. So this is a total signal for the target. So we can also define the total power budget for the terrestrial, this one, and this is a receive signal at the base station from the particular target in a terrestrial scenario, and then we can define this one, or you can say SNR of the target TB will be given by this 4.11. So then in a downlink case, so here because terrestrial network also serve multiple downlink users, so this will be received signal. So this is a desired signal, multicellular user interference, sensing, satellite interference, and the noise, and this will be SINR. So here again the target is to maximize the total sum rate. So that means satellite as well as terrestrial base station under the QS for the satellite, terrestrial, power constants at satellite, and power constant LEO satellite, and power constant at terrestrial base station, and this is a phase shift constant, unit modulus phase shift constant. We deploy it in a terrestrial case, so this phase shift constant for this. Now, if we see, if we use this, the conventional method to solve this problem, the complexity will be very, very high. And also this problem is non-convex due to the coupling of variables along with the ratio of the variables and the unit modulus constant. So you can imagine if you increase the number of phase shifts, the complexity will become very high, or if you increase the number of users, again the complexity will become high. So here we can, let's say, so here we proposed, let's say DRL. Okay, so DRL based algorithm, you can say. So here we implemented, let's say, okay, we adopted DRL framework where we define again the MDP framework, where there are three state major components: state, action, and reward. So again here is state space. We can define this will contain both. You can say all the channels here, weight vectors, as well as this uh, So this one is the first one is a LEO satellite. This is a satellite part, and since there will be a you can say a decoder, so that will also be part of this state action, and this is a this is a okay. So this is another one more parameter. So this will be also related to the satellite. Similarly, for a terrestrial scenario, and then we can also define action space for both satellite and terrestrial or base station. We have weight matrix. This is W, capital W. So here we have defined capital W. And U. And but in case of this base station or terrestrial, we also, because we are deploying phase shift, so I mean RIS, so there will be also phase shift, and then we define the reward. We have this one gamma RT minus I. So we have a different at a different time steps. So again, this gamma is binary 0 and 1. So this one is we propose federated DRL algorithm for each agent. So we process. Okay, I mean we can follow the similar approach like the previous one. So we compute first initialization, give some input, and define some initial parameter. Then define the number of epochs. So we are let's say 1 to E is maximum. Then we initialize some parameter, and then here we perform the inner part of this MDP. You can say, for example, obtain action from the actor network, then add the exploration noise, then compute the instant reward, observe the new state, and then we store the experiences in the buffer sample, and then again we return expected return this YT. Again we have we again update the this target actor and critic actor with these two parameters. So we repeat this process, and finally we update this parameter row, and then we process this one until the convergence. So here we have let's say some simulation results. So here we can see this federated DTPG, or you can say this is a kind of let's say yes. So this is a distributed scenarios. So here federated we have a DDPG, and also we compare with DQN, and for a different row parameters. So here you can see the proposed one is or all the algorithm converges within a 2000 episodes. So in second figure we show total sum rate versus reflecting element. So again because as we increase the RAS elements, so we have a diversity gain, and due to that with optimal one you can see we can have a significant gain when the RAS elements when RAS element become untapped. However, in case of random, if you see random is performing almost giving the fixed value throughout this RAS element, because this is a random, so it's not necessary to get the optimal optimal value. So maybe here some value will be slightly better, so we have slight gain. And this is without RAS case with DDPG and DQN. So again, this one is okay, perform worse than this random. So that means this one is we are optimizing only digital, only precoder vector, not a phase shift. And this one is optimizing both phase shift as well as the decoder. So here in right side figure, so here average sum rate versus transmit power, and here we have average sum rate of CU, and this is SU. So that means because we have two kind of users, so user served directly served by the satellite, another served by the terrestrial network. So here, because we can see some trade-off, this is a transmit power at a satellite. So when we increase the transmit power at satellite, so the performance of satellite user will become, or satellite system will become better and better. However, the performance of terrestrial network will fall. So reason is that because there is a interference from the satellite towards the terrestrial network, so that impact in the total sum rate loss. This is a impact of target SNR. Again, this is for terrestrial scenario. So as you increase the threshold, here you can see the total sum rate will decrease, slightly it will decrease. And this is a without sensing, so the this SNR, the target SNR will not impact on the cellular performance. So here we have a constant performance for the cellular systems. So in 4.6 here we have shown the impact of antenna M. So again here as we increase the antenna M, so we have diversity gain or transmit diversity gain. That's why performance in all cases is improving. However, again the DTPG, federated DTPG provides best performance or outperforms the rest of this. Here we also implemented so the central DTPG. So this is a central DTPG. This is central DTPG, and this is a federated DTPG. So that is distributed. So here, if number of antennas become made, so the performance of proposed one and central are same. However, in terms of complexity, you can see the in case of central complexity will be very high. So, for example, here we can see execution time versus this for various algorithms. So here you can see this is federated DQN, federated DDPG. This is a central DQN, central DDPG. So here you can see the execution time for this proposed one, federated DDPG and DQN, are much lower than this central DDPG. So in terms of you can say almost 3 times lower than the central DDPG and DQN. So this is a huge advantage over the central. So and along with this, we can maintain the privacy of each user because they process the data locally. Now this is the last work. This work published in IEEE Transaction on Cognitive Communication Networks. So this one is an extension of the previous work. Now here, instead of maximizing the throughput, we want to minimize the total power. So in fact, here we wanted to show the trade-off because if we minimize the power, then the terrestrial power, I think. So then how it is impacting on the satellite users. So here we want to minimize the total terrestrial power under same constants, terrestrial and satellite constants along with satellite power constant. Because this objective function will impact on the terrestrial, satellite part. So here the process is same. We can say we define the state, action, and reward, and the algorithm will be same. So only the reward will change, and now here we have some results. So here we can see this is a transmit power, and we have compared with federated DTPG with central DTPG. So again, the federated DTPG, this one is consuming very less power in order to achieve same performance. So yeah, and here in second figure, here you can see here we have a transmit power versus this is a target SNR. Of, I mean that fall in served by the terrestrial base station. Again, as we increase this one, so in case of no sensing, so required transmit power will be very less. You can see. So, but since uh, we have, I mean, in this case, only it serves the users, no target detection. However, here we can see federated learning with random phase it consumes more power because we are just optimizing the weight vectors, not the phase shift. But when we optimize the phase shift, let's say with optimal phase shift, we have significant, we reduce significantly in power consumption. So from here, let's say when target SNR is 14, so it was 25 dBm required power. Now it become around 23 dBm. So similarly for other algorithms. So last one is here we show the impact of number of antenna, transmit antenna at the base stations. Again, due to diversity gain, the required transmit power will be lower. And with federated DDPG with optimal RIS, we need lowest power compared to the DQN, federated DQN, and no RIS scenario. So here we consider, let's say, two target case in both satellite for satellite as well as for this terrestrial case, and we have plotted this beam pattern again. So here you can see we have a perfect, gain for target 1 as well as target 2, and similarly for this is for a terrestrial scenario. So where this beam pattern gain is given by these expressions. So here, okay, so the okay, just now I want to summarize these previous two works. So here you can see the proposed federated based DDPG outperforms the conventional, let's say, DQN, federated DQN, as well as the central DDPG in terms of both power minimization as well as the total rate maximization, as well as the computation time of the proposed federated DQN and DDPG is almost two-thirds lower than the conventional central DDPG and DQN. So this was all about my talk. So if you have any questions, you are most welcome.
Participants, if you have any questions, please raise your hand. Or you can also unmute yourself and please ask your questions. Any questions, participants? Okay, if you have any questions, you can also later on you can write to Dr. Singh, or you can also let us know and we'll forward your questions to Dr.
They can,
Singh.
okay, I will share today's slide.
Yeah.
Except first paper, they can download remaining 3 papers. All 3 are published. So you can just forward to them. If they are interested, they can go through the paper. If they need a code, I can forward the code for them.
Okay, great. Thank you so much. Thank you so much,
Okay,
Dr. Singh.
okay,
Thank you so much for your time. So we have some time before our next session begins. So Anshuman, when does the next session begin? 4:30 or 5?
Next session also will start 5.
5. So we have some time since Dr. Singh has finished little early. So we'll take a short break here, and and we'll start again at 5 p.m. when the speaker joins.
Okay. That will look.
Yeah. In the meantime, let me also tell all the participants that after the last session, we'll be having a short quiz and followed by the valedictory session. So the quiz will be in online mode only, and we'll share the link with you. And you'll have to answer the quiz within the stipulated time. Okay? Hopefully that's clear for everyone. And only upon, as per the AICTE norms, so you will be given the certificate only if you pass the quiz and also if you have the requisite attendance. Anything that I'm missing, Anshuman?
No, it is okay. That's fine. So we can take a break for 10-15 minutes. Then I can explain 10 minutes for the exam related.
So what time the exam starts?
Exam 6:30 p.m. we will start. Already I circulated the message to WhatsApp.
Okay, great.
To all these participants. Again, I will explain maybe 10 minutes after break. 10-15 minutes I will explain details about the exam and all of that. Right?
Great.
Any questions? Okay, so participant will take a break of 10 minutes. Then after that, we'll come back and we'll discuss the experience of your journey in this particular program. Typically, what is your feedback and all we will discuss a couple of minutes, and also I will explain today exams, online exams that will start from 6:30 p.m. to onwards for 30 minutes. Exam will take. So all this information I will circulate to all of you. Then our last session will start at 5 p.m. and then finally today we will conclude the whole session. Okay, we'll come back after 10 minutes.
Hello, sir. Hmm.
So, welcome back, participants. So, we have with us our third speaker of the day, and this is the last session of the day as well. So, we have Professor Bhatia with us. So, you will know Professor Bhatia since he has already given a talk earlier on the 11th. I'll just briefly introduce him. Just so that you can refresh your memory. So Professor Bhatia is currently working as a professor with the Indian Institute of Technology, Indore, and is also an adjunct faculty at IIT Delhi and IIIT Delhi. He received his PhD degree from the Institute for Digital Communications at the University of Edinburgh in the UK. And during his PhD, he also received the IEEE Fellowship for Collaborative Research at the Department of Systems and Computer Engineering, Carleton University, Canada, and is a young faculty research fellow from MIT Government of India. So he has published more than 420 peer-reviewed papers, and he has also filed 16 patents, out of which 10 has already been granted. He has supervised several PhD students and master students. He is currently a senior member of the IEEE, fellow of IETE, and a certified Scrum Master. And he has been mentioned among the world's top 2% scientists by the Stanford University. So without wasting any more time, I would like to hand over the microphone to Professor Bhatia. Over to you, sir.
Hello. Yeah, thanks so much, Professor Deep, for the nice introduction. I'm audible?
Yes, you're audible. Yes.
Okay, perfect. Thank you. Thank you so much for having me over. And as I learned, this is the last day of the FDP. So yeah, thanks and congratulations as well for conducting it successfully over the last few days. So we are at the last session. So I'm going to present a talk. So I'm going to skip the introduction because we already had it in the last session. So I'm going to jump straight to the topic of the talk today. I have it in my PowerPoint. I'll just make it full screen. Used to be Control L. Control L. Yeah, it is full screen now. So I'm going to attach it with this process. Yeah, can you see my slides now?
Yes, it's visible. Yes.
Perfect. Thank you so much. So I'm just going to switch off my video. The talk is there to save the bandwidth, so I'll just focus on the talk. So thank you so much for being here. And this is a new topic, visible light communication. So visible light communication. I'm not sure how many have worked on or heard about this term. So we'll start with a small introduction of what is visible light communication system, why it is important. Then, this again, it's a talk for about hour and a half. So we'll also get to know what are the major companies. So this is like no longer like a sci-fi concept. It is something which is in practice. There are companies making products on Li-Fi. There are some trials that has happened. There has been successful implementations. I have some links or videos where they have installed a visible light or Wi-Fi setup. So you can see that as well. I think for audio, we'll see how it can go. Sometimes, if I have my headset and it doesn't go, but let's see how that comes when we hit that slide. Then we look at there are various practical challenges that still exist with visible light communication systems, and we've seen there are various solutions for it, and we have also proposed certain solutions for tackling or handling these problems that we occur, which limit the performance of visible light communication systems. Like any other communication, there are certain issues that needs to be tackled. So that's where we have been working as well for almost like a decade now, close to decade. Yeah, almost a decade now on visible light communication. So now let me change my slide. So VLC has emerged as a promising green and interference-free supplement to RF based systems. I don't know how many of you know, so we'll start from very basics. So VLC relies on intensity modulation of LED according to the input message. So very simplistically, we have in the last decade or so, just about a decade and a half now, we started to move away from incandescent lighting to LED based lighting. So our tube lights, bulbs, they're all now LED based, right? In the hardware, we have replaced our bulbs with this LED as well. So we can use these LEDs for communication purpose too. Simplistically, if we can switch on and off, this is very simplistic, on off keying. So basically what you can do is switch on and off the LED very fast, so that to a human eye, we don't perceive this on and off, we perceive that it is continuous. So our perception says that your light is always on, but in practice we are switching on and off the LED, and that um, can be used for communicating the message. So we can maybe have on is 1 and off is 0, so we can transmit these bits once and the receiver have a photodiode which detects if there is a 0 or 1 light or not, and then if its switching speed is very fast, it can detect that 0 or 1 has been transmitted. It's a very simplistic view. You can also create a small setup in your lab by using an LED, but I'll suggest use a bunch of LEDs or a lens or something to concentrate all the energy towards one photodiode, and then use the photodiode to do the detection. Now, visible light covers the wavelength from 380 to 750 nanometers. So this is our visible spectrum. So if you look at, we gamma rays, X rays, ultraviolet, then infrared rays, radar, FM, TV, and TV and shortwave, AM. So we have these different bands available. Now of these bands, um, um, there is this wavelength that is available for visible light. So this wavelength is for visible light. If you go beyond, there is infrared, another type of rays. But our interest is here from 380 nanometer to 750 nanometers, which is huge. It translates to 430 to 770 terahertz. Now this bandwidth is really huge. So if you compare now with your 4G, 5G systems, we have bandwidth about 6 megahertz is given to each user. I think Wi-Fi is about 20 megahertz or so. So this is like 430 to 770 terahertz. So we have a lot of bandwidth. So we can allocate a very high bandwidth to each user. This is all non-licensed. So what does that mean? It is non-licensed. Now, you see, for the case where in the telecommunications, we have broadly a licensed free and a licensed bands. The licensed bands are, you would have heard about, see in India we talk about 2G, 3G auctioning, 4G auctioning, 5G auctioning. So these are the bands, so where the government, they would put these on auction. So different wireless providers, cellular providers like Airtel, Jio, Vodafone, Idea, they will bid with BSNL, they will bid for those bands. And yeah, typically, they will all, just like any other bidding, they'll bid for the good bands and the bandwidth that they would like to use in a specific region, right? These go in crores of hundreds of crores of rupees for the government. They give a fee to the government, and that comes down to the customer as a charge. And when we purchase the SIM card and services from the vendors. So now these are licensed bands. So here, as a researcher or a user, I cannot transmit in those bands. And there are again some bands which are for specific purposes. So like for defense, for air traffic control, or others. So I cannot, none of us can transmit legally. So it's illegal to transmit in those bands. However, we can receive it. Hello, can you hear me? I think someone got unmuted. Okay, so yeah, this is about the licensing. Now then there are unlicensed bands. So typically got ISM band, so for instrumentation, scientific and medical use. So if let's say you are using your Wi-Fi at home. Right? So you are also transmitting RF signal. Now, in that acts like a base station, you can say, because so many devices they get connected to the Wi-Fi modem. Now, let's say serving 8 users or 16 users, so it is also like a small base station, but the difference is it is working in the ISM bands. So it is not work. It is not. So you don't need a license to install a Wi-Fi modem in your home and anywhere in the world. Uh, and similarly for some of other bands as well. For example, when you're using for car keys, automatic keys and all, so they are also gate opening, so they all work in ISM bands. For medical use, they use ISM band. So there's no need to purchase a license from the government. Otherwise, if you want to, have a base station which is serving, let's say, your university or somewhere else like a private network, so you need to purchase a license from the government. Now, visible light. So for now, like for example, like you put a LED lighting in your home properties, so you don't really need, you don't take a license from the government. You install so that's the advantage. The visible light works in a visible light communication also works in a non-licensed channel. Now, it is also low cost and easy implementation. So non-licensing becomes, makes it easier and democratized. So that's where the advantages are. Same thing with Bluetooth, same thing with Zigbee and other wireless standards, and LoRa, and also where you can use the products wireless, but in a ISM band. Then it has a low cost and easy implementation since it utilizes existing LED infrastructure lighting. So we are already putting LEDs for lighting, be it street lights, be it in our home, offices, campuses, right? So we can use the same infrastructure for communication as well. So there's no specific, separate transmitter receiver you are putting. It is energy efficient because it takes less power than RF, and also it is green because we're using for lighting primarily, and actually for lighting we use a lot of in terms of communications, it is a very high SNR, signal to noise ratio, which is good for communication, and that's where VLC has an advantage as well. That we usually have a lighting which is quite bright for us to read, and the same intensity of light can be used for communication as well. You don't need to increase it beyond that. Then actually there are some works which look at the dimming. So in fact, when you have lowered the power levels, or even when to a human eye, it seems that the light is the bulb is switched off, but it's still, let's say, transmitting wireless communication signals. So for eye, it may seem like it is dark, it is switched off, but in fact it is still on and transmitting. So that's in dimming also we mode also this can be used. Now it is immune to interference from electromagnetic sources. So a lot of the interference that is generated in the communication systems comes from EM interference. Be it from machine motors, man-made or natural ones. Natural ones, okay, like and all they are in the silicon, so that's there in visible light as well. But other which are man-made, they don't exist or interfere with the visible light. And it's another advantage that because it's highly secure because a visible light is confined to the opaque boundaries, right? So it does not pass through the wall. So the window it can be, but if it's in a window, then you may see a eavesdropper, trying to get the signal or eavesdropping the signal. So it is by nature it is quite secure because it cannot penetrate through the opaque boundaries, so like a radio frequency signal. So that's another advantage of using visible light communication. So it has a threefold goal of illumination, communication, and energy harvest. So we can actually use LED, solar panels as well for communication. So you are using, let's say, a laser or a bunch of LEDs for transmission, and solar panel is doing energy harvesting plus also doing the detection. So it serves as a very important aspect for green energy harvesting. High SNR, as I said, for illumination level, we actually typically use quite a lot of a very high signal to noise ratios in the visible light communication. That's because, again, for human eye perception, we typically have very high lumen levels. Now, applications for visible light is in we can call it light fidelity as well, so Li-Fi. It is there in smart lighting. It is safe for use in RF sensitive areas like hospitals, aircraft. So if you are traveling by aircraft, especially when it's landing and taking off, we are told to switch off or put our phones in airplane mode, right? So now all the smartphones, they have this airplane mode. It is again for a purpose that the RF radio frequency transmission can interfere with the communication system on board on the airplane, right? But which is not a problem with the visible light, because it's a completely very different band. In fact, there is I don't think I have put in the slide, but there has been talk of putting these VLC based systems inside the next generation of airplanes. So that allows you to do communication at the same time as when the systems are then the flight is taking off and is landing. Then again, it can be used for intelligent transportation system like vehicle to vehicle. So I think there are some slides where we'll go over them in detail. IoT-based application very popular in IoT, and also now there's in wearables. Now, this broadly puts puts various applications of visible light systems. So if you look at personal area network, so we can have conference hall. So we have lighting on the ceiling of the hall. I have some slides which show you what physically it will look like. Then we have transportation hubs like airports. We can have it in shipping hubs and trains. In the metro train, you have the lighting. So if it is within a tunnel or so, it can provide communication systems by using the lighting infrastructure. Home or office, we have lighting on the ceiling. We can have these spots, small lamps for reading that can also be used for communication. Data showers. So, for example, in a smart city type of environment, we have these street lighting that can be used for data transmission as well. Intelligent transport system. We have vehicle to vehicle. So one front is talking to vehicle in the back. So we have the front lights are based on LEDs as well. So that's what has also happened in our 2-wheelers and 4-wheelers. Also, we get LED lighting. On the back panel, it could be photo detectors, so that are detecting this. So we can have communication between the vehicles as well. Oh, sorry, I'll go back. Vehicle to infrastructure, so it could be on a roadside unit, which can communicate with this, or it could be the small information it can give, like for example, how much traffic is there, maybe something local about the city or the area, what is happening through the traffic lights that are installed, or the signs or stop signs or the signs that are there. So that's called as vehicle to infrastructure. So it's not vehicle to vehicle communication, it's vehicle to infrastructure communication. Then it is very popular and very important use is in non-RF environments. So for example, in mining or we see sometimes some videos showing at a petrol station and all where RF could cause fires. And also that's where we can use our chemical plants. We can use visible light. EMI sensitive like hospitals and all where we can use this in airplanes, already said. Security, because it's visible light cannot pass through the opaque boundaries of the wall, so it cannot be eavesdropped. Then underwater system also is quite popular. This is another application, so it works actually very well in underwater as compared to other forms of communication systems. So it can be used for smart lighting in infrastructure. There is a small video I can show in one of the supermarkets, like in India we have big bazaar, D-marts and all that we have. It's some similar supermarket called Carrefour in France, where they have installed the system based on visible light using Philips system. and the user uses their handset, our smartphone, without any additional device for receiving. So we use our smartphone screens, put an app there, you can make shopping lists and it can direct you where goods are and also help in billing. Augmented reality, again, we need a lot of bandwidth for it. Entertainment, of course. Then short range communication, replacement for for cable. So if let's say you have a data two big servers, they can communicate using visible light, or they're using optical communication, within the server or even outside the server as well. And then there are various smartphone applications. We'll see a few. Now, one of the some of the major companies in this area is Li-Fi. It is founded by Professor Harold Haas. He was with University of Edinburgh when he founded this company. It's largest, or the biggest of the VLC companies that are available. Firefly Wireless Network is a VLC and infrared lighting company owned by Light Ponte, based in France. Then we have Oldecom, is again a French telecom company that began its research in Li-Fi in 2005, also based in University of Paris, Saclay. Then we have VNL Communication, which is based in the US. And then there are other players as well. For example, we have Signify, Lumen, and in here you'll find Wipro. So Wipro has been a big player in lighting and also in IT systems as well. So it has also ventured into the visible light communication systems. There are new products in the market that are getting available. So new Li-Fi products are getting launching faster than ever before. A lot of companies are working on Li-Fi and improving the technology. So some of these products we'll see in the picture as well, how they look like. This Li-Fi Max, My Li-Fi, Li-Fi Care, and there's this other for securing vehicle and others. So for example, My Li-Fi, this is like your personal communication device. So each user can connect to the internet through this optical signals emitted by a tabletop desktop lamp. So it's like a small lamp. You have this, an optical fiber wire coming, and then you get this output from the end. So this can have up to 7 connections, just like your Wi-Fi modem, and it provides transmission speeds up to 23 Mbps. So very high speed, and it is RF free. So some people have concerns about radio frequencies on our health. So this does not use any RF at all, but provides us at 23 of wireless speed, 23 megs. We can use products like Li-Fi Max, which are like these lighting systems, and you can see there is a small place where you can put the RJ connection for your for your LAN, and this you can put on the ceiling, so it is fast, secure connection, free from radio waves. Plug and play system, you just install this lighting on the top and connect to your LAN cable. Guarantees fast speed of 100 Mbps download, 100 Mbps upload, compatibility with various operating system. Li-Fi Max can provide access to up to 16 users at the same time. Right. So we can have a small device like a dongle-based device. Well, I'll show you in the next figure. So Li-Fi Care is something that can be used in the hospitals by medical professionals to gain timely information. Also, where RF is prohibited, so we can use visible light system based. Now, this is a typical dongle. So, for example, now if you recall, few years back, we used to use, before we started using hotspot on our phone, some still use a dongle-based device where you put a SIM card inside the dongle, and that acts like a transmitter receiver, and we connect to the cellular network and do browsing on our laptop. So similar concept, we have a small USB type system and a small lens through which the communication uplink and downlink happens. So this is again a product from Pure Li-Fi. We can introduce this dongle to our laptop or other devices, and Li-Fi provides uplink and downlink up to 42 megs. It is fully compatible with Windows and a different operating system. So it's a plug-and-play device. you can put it in your laptop or other device you want to communicate with. Vehicle secure works on the vehicle to vehicle, between the vehicle to communication. So interconnectivity between transportation units be used. So vehicle can connect to the traffic signal. It can connect to the next vehicle or other infrastructure for both communication as well as for safety terms. It can also have alert systems based on visible light communication systems. Firefly Li-Fi provides a great solution for navigating cars in the urban areas. So, for example, you are trying to communicate in a parking lot as well. So that's where you have lighting infrastructure. Sometimes the signals are not so good; they are underground parking, but then you can use visible light for communication and positioning. Office secure links. So this is again showing you that you can have the office lighting, and then you have these different devices, including your HDTV and laptops, which can connect to the uh, lighting infrastructure. So this is a secure link within the office environment, because again the lighting cannot go outside the room. It's green, blue, different types of colors are mixed together. It can provide a multi-point to multi-point type of applications for again indoor conference room and offices. Again, this type of lighting can be used. Luminex Li-Fi, it can provide up to 70 mega Mbps for downlink and 60 for uplink. Covers an area of 400 square meters. So if you have a small, small room like a studio apartment or a small shop, one light is good enough. It provides lighting as well as can connect to 15 simultaneous users. So you don't need a separate, Wi-Fi connection. No, it is not limited. So it is something different. But here, instead of the visible band, it is a laser that is used. But as again shows that your optics can be used for communication. So in the islands of Orkney Islands, is slightly off the mainland Scotland, there was this trial done by 5G Rural First, University of Edinburgh, BBC, and all. They were able to do a FSO link between and with the solar panels, doubling high-speed connectivity to this island. So this map shows that it is off the mainland, Scotland, and the transmitter is on the mainland, and the receiver here. Well, it does both ways, but just for illustration, I'm telling. And it can connect 389 rural towns with the slowest speeds. They were upgraded using this 5G first system. The test showed promising this, and this was again a trial run by University of Edinburgh Pure Li-Fi, with support from Orkney Council and other Project BBC and others. They were supporting this initiative. Then 6G flagship in Oulu in Finland, they have been working on this for very long. So this small demonstration, let me see if I can show the video. Just let me know if this is going to be visible for you. So I'm going to allow it to open. Let me see if it opens. Yeah, it has opened. Can you see the video?
It's static.
Static, okay. Let me connect this. Maybe I need to connect a different browser. And I will try to check if the audio is also available. So let me first connect this. Let me use browser to do. Maybe I use the same browser. So okay, there's some advertisement. I'm just going to skip this. Okay, so let me make this full screen and connect. Okay, how can I connect? So, okay, my compact view. Okay, so here I think I have so where's the option to connect? Stop sharing. Okay. So I need to stop sharing and then connect to the browser. Okay, there's still people joining. Okay, let me connect to the screen. Okay, visible light, visible light, visible light. Okay, that's the video. So you can see the video now.
It's still static.
But do you see the video screen or do you see the?
No, I see the video screen. So it says SIG flagship. Yeah, it's playing. Can it play now?
So let me play it back. Yeah, and let me know if you can hear the music. Now, can you see the video moving?
So it's on the screen. It's on a static screen of 6G, the next generation of mobile connectivity.
Okay. Yeah, perfect. So I'll keep on playing. And were you able to hear the audio as well?
No, the audio is
The music.
not. Audio is missing.
Okay, so for that, I think I have to take. I'll remove my headset, and then this should be okay. So now, can you hear me? Yeah. Hello? Hello, am I audible? Hello?
Hello, sir. Hello, sir.
Yeah, okay, thanks.
Yes.
Okay, thanks. So the video you could see and also listen was the voice.
Yes, you're audible, sir.
Okay, perfect. So I'm coming back to my slide. There's
Yes.
another video later which shows the demonstration in persons. So so this is one example. So Professor Kaz was that that it can be used for both radio as well as light together. It can be used for communication because there are some places, some use cases where you may not have a direct connectivity with the lighting-based solution, and then there you can use RF as a solution. Okay, so now this is another one, another small video. So I'll do the same thing again. I'll open the browser, connect to this link. So this shows that in practice, they use in Lyle, a small, a big, not so small, but it's a big, shopping center. So in the shopping center, we have installed this visible light communication system with Philips Lighting, and they show it works. So you can actually use it for communication and positioning. So yeah, let me write this. Oh, where is it? Just a minute. Yeah, I'm just changing. Why it's not closing? Yeah, okay. So on the browser, just going to attach it. Let me. So now I'm going to connect this. So okay, switch off the video. Connect this with the browser. So you can see Philips. So play it.
The sound is not coming.
Okay, so you could see the last video, right? And here as well. So I'm going to share, assuming you can listen to me, I'm going to connect to the slides back. So this showed that, yeah, this is, not only, a sci-fi concept, it is out from the, from books and the papers to real life, demonstration, not even prototyping, it is actually getting installed. So it has, in the Carrefour kind of application, it helps you in connecting to the shop floor, connecting to different products. The positioning is very, very good in case of Li-Fi. So Li-Fi brings an opportunity for malls and other centers to help include, in the user experience pulse. Also, it can help in the inventory management, finding out where the goods are. For example, if you have a very large store like Flipkarts, Amazons, and all, they have big dark stores where they can, or even big warehouses where they can pinpoint or come closer to where the actual product lies. Um, Now, this is all the good things about VLC, I'll say. Then there are practical challenges that are there in implementing these, and having a very high bit rate. Um, Visible light channel is impaired by LED nonlinearity. I suppose my slides are visible, right? And they're changing. So I'm on slide 26 on problem formulation. So we have LED nonlinearity as a big issue, because LED by design is a nonlinear device. So the VI characteristics are not linear. It's based on purely on the silicon behavior of the silicon. Then ISI, it can also have inter-symbol interference, again similar to the case of RF communication. We are also limited by dispersion of the channel and limited modulation bandwidth for LED. Then user mobility. Now that's another factor. Even a smaller mobility can cause Doppler shifts. So hence, in our recent work, we have explored using OTFS for visible light communication, and also I see the group in IC Bangalore also looks into the OTFS in this area of VLC. Then there are other issues for DC bias error term that comes in, because the DC power may be fluctuating, and that may impact the detection of the symbols. Now, visible light has various challenges, impairments, which significantly degrade the bit rate performance. It causes significant performance gaps between the promised and the achieved throughput. The throughput of existing VLC can be increased by using a massive MIMO type. So generally, when you look at a LED bulb, you can remove the top cover and the shell, which is typically white in color. If you remove it, in the base you will see it's not only one LED; it's a bunch of LEDs. Not like the LEDs that we use it in our breadboard type of experiments. They are silicon, very small ones. Just like on a PCB we see resistors and LEDs or something similar. It's very small, but then it's a bunch of LEDs. It's not only one LED, but there'll be 12, 10, 15, 16 LEDs. So it can be used as a massive MIMO system. So in case of visible light, massive MIMO is not 100, beyond 100, but it is a lesser value is assumed to be okay. Now, in case of visible light communication, the performance of massive MIMO has this limitation that because LEDs are very fast, close to each other, then there's a general ill conditioning that happens, which doesn't give you. So basically, the channels are specially correlated, which decreases your system capacity. So inversion of a ill-conditioned channel matrix, however, results in noise amplification, which also degrades. So given the solution can have another problem, just like zero forcing type of case, where you can do this, but then there are chances of doing noise amplification as well. So we need to look at different solutions to fix this problem. To mitigate these issues in VLC's impaired channels, we have pre-distortion, post-distortion. So pre-distortion we can do at or pre-coder we can do at the transmitter, and at the receiver we can do a post-distortion, like we can use equalization to do it. Now, again, in the literature, largely, I'll say, there are three different research groups exploring in three different philosophies. The one research group by Al-Ghala uses, it proposed a LUT, a lookup table-based solution. It's a very simple classical solution, which is, so LUT is, very commonly used in industry in many applications. So they proposed something similar to be used. This paper came out in electronic letters more than a decade ago, but very simple solution. So for example, if you already know your transmitter receivers, right, you already know their characteristics from the data sheet or the graphs are given, you can create a lookup table and use that lookup table at transmitter to find to the pre-coding. But again, that's not suitable for dynamic environments. It's not portable and not fixed for that particular LED. Right? Whereas in practice, there are no system is dynamic. There will be other environmental factors as well. And tomorrow you may change the replace the LED transmitters as well. So it's not really scalable, but very easy, simple solution. Kim team, they have been looking at adaptive solutions. So that's where we have also been looking at. But they've looked at normalized least mean square type of algorithms with to track the LED nonlinearity. Now this delivers a suboptimal solution, but one of the major limitations is that we are trying to do this, finding this, fixing this nonlinearity by using a linear structure. And that's where we came in with my student Rangit. We explored looking at adapted Chebyshev-based architectures. So the Chebyshev filter is nonlinear in structure. So we said, okay, why don't we use a nonlinear structure to do pre-coding in a nonlinear setting? Because we know it's nonlinear, but linear in theory we need infinite number of terms to model the same type of nonlinearity if you do the reverse of it. So the reverse also will be nonlinear characteristics. So there, if you use a nonlinear characteristic, and then we can use some criteria to learn the stuff. So initially we used LMS itself as a learning criteria, but our structure for the pre-distorted was based on the Chebyshev filter-based structure. Then we can also use pre-distorter. We can also use post-distorter as well, because pre-distorters, they rely on the feedback from the receiver as well, so which may or may not be accurate. But yeah, but in practice, both the things are used in even in RF-based wireless as well. So then let's look at both distorter or equalizers. So here again we found largely three different groups, different philosophies. So one is from Stepniak. They used the classical solution using Volterra DFE. So Volterra DFE is a classical filter structure. So Volterra filter structure and DFE is where the equalizer is formed. So we Volterra DFE or Hammerstein-based DFE. They're based on polynomial series expansion. They are again the classical solution used very much even in optical communication, optical fiber communication, and also in VLC Stepniak team has applied. It has high computational complexity and also modeling errors, because again we are trying to do a polynomial fit to a nonlinearity. So typically for Volterra filters, we go only up to second order. We don't go much beyond. We can go to third, fourth, and that's where the problem lies. Maybe the up to second order is not good enough for modeling this type of nonlinearity. So in that case, these algorithms they fall short of and they have this modeling error issue. As we came from the philosophy of using kernel-based LMS or kernel-based MSCI criteria, so different criteria, least mean square or minimum similar criteria. That's also very interesting. But we worked in KHS solution. That's where the rest of the slides will focus on as well. RKHS is reducible kernel Hilbert, reproducible kernel Hilbert space, or reproducible kernel Hilbert space. So these algorithms they perform very well. They deliver suboptimal, but then again they can be improved. We have improved on these. But the advantage is they can model, in theory, any arbitrary nonlinearity, and that makes them very strong for a system where there is high nonlinearity. So we have applied this philosophy or this type of algorithms to in radar signal processing as well, applied to wireless as well. So wireless means wireless RF based communication system. Again, we knew that the nonlinearity is a major factor impacting the performance. Then there's another team from Northumbria University, Newcastle, north of England, by team with Gazem Loy. Their focus has been using ANN type or DNN type of equalizers based on neural networks. They have limitation. Then they have difficulty in non-convex problems, computationally more complex, sensitive to hyperparameter tuning, and it's hard or not possible at the moment to. We also not possible at the moment to give guarantees. Whereas for our system like RKHS based ones and Volterra DFE based ones, so there can be guarantees given that yes, the algorithm will converge in certain iteration. It will converge within this error range. We can give indication on the memory that is required, and if you reduce the memory, then what happens? So there are various things which are good for a system implementer which can be done. Whereas based on deep learning or type of criteria, it becomes impossible or difficult or just basically impossible to give you guarantees that it will definitely converge within these number of iterations or within this much compute will be required to get the best performance. So hence we move to RKHS-based solution. So RKHS-based post-starters are found to outperform classical. That's why we went through it. We're still using them. Almost like again close to a decade. We're still using them. They have a desired feature of convexity. It can do a universal approximation. So any kind of nonlinearity can be modeled. It is low computationally complex and it can achieve low complexity using sparsification. So I'll cover sparsification later how we do it. This is also used in machine learning. In certain cases, you can use for deep learning as well. However, the conventional feed-forward RKHS-based post-starters are found to deliver suboptimal performance over multipath channels. So we have considered ISI, high SI, and non-Gaussian distortions as well. Now, why you call non-Gaussian distortion? Because you may have sunlight, you may have impulsive noise, which are non-Gaussian in nature. Although, like most of the research papers, 95% or even more, assume the system to be affected by only Gaussian noise, but in practice there are more different more types of noise which are not Gaussian in many application areas. So here our motivation has been to look at again another criteria is the cost function typically used in adaptive signal processing or even in machine learning also is based on MMSE criteria or minimum mean squared error. So what we try to do is we try to we have a squared of error. We try to minimize it using some algorithm, but our focus is largely on doing a minimum mean squared criteria. Now we can. So when I'm doing a equalizer, right, design, or I'm at the receiver, my focus or is to minimize the symbol error rate or bit error rate, right? In other terms. So why do I need to minimize a mean squared error? Yeah, although in certain cases it is can be mapped, but it has been found for last 20 years or so. It has been found that more than that, around 30 years ago, it has found that the symbol error criteria is more stronger than the mean squared because it incorporates all the statistics of the system, so all the noise and these additional processes. Especially if it's a non-Gaussian noise, then MSE is not the criteria to be used to give you optimal solution. So that's why we look at MSER or MVC is something that we have recently started to explore, is looking at maximum reservoir criteria. We have some papers in the literature, you can always refer to them. So we have designed our post starters based on the RKHS based criteria. Now further, RFF is a random Fourier feature kind of structure can also be used. They give you better performance in case of a finite memory budget, and that's what it is in practice. The budget for compute or designing a system, you have a finite memory and a finite compute, right? So goal of work has been to look at new algorithms for better post distortion in high ISI and non-Gaussian narrative systems. Now, largely the problem is to look at LED nonlinearity, ill conditioning of massive MIMO. So even if we can improve the condition number, then we can increase because we are having more of these independent paths. So and also handle DC fluctuation. So let's look at the system model first, and then we see how the solution are. So and then again details are given in this manuscript. Now we have a look at a hybrid adaptive structure with precoder and post distorters together for massive MIMO. Now to mitigate LED nonlinearity and reduce the condition number, we use a RKHS based solution. So this is our system architecture, and this algorithm and the other we use it is a supervised learning or training based system. So here initial few bits or symbols are known to the transmitter and the receiver, right? Which is a very commonly used system in our Wi-Fi and cellular networks. We will also look at, I think the last one is on blind or unsupervised learning, which gives you a higher system capacity, but the problem is that it takes longer to learn. But then there is no wastage because all the bits that you are transmitting are going to be used for communication purpose only. Right. So here, if you look at this transmitter and receiver design, a very simplistic block diagram where we have a precoder. Now precoder has certain weights per ton. Now these weights are done based on some value of lambda, which is coming from the receiver. So assume there is a signaling channel which can transmit this information, and then there is a DC bias added. We use a Capcom type of modulation scheme, and then followed by an LED array. So LED array will have as a function f mentioned, which will introduce the nonlinearity in the system. It goes through the channel, which has a massive MIMO channel, and then the AWG noise gets added to it, red white Gaussian noise, and then we have photo diode, which acts like a receiver, and then we have when we do an SVD decomposition, so we have other components as well. So this is the first part. This is the second part. We estimate it. We have an estimated symbol which is detected using the post starter, and then using the KMSA criteria, we estimate X. So X was transmitted, XK, and we get X hat K at the receiver. And then there's some feedback which is given to update the precoder. So this is the overall design, which is a training based or supervised learning based solution. Now let's look at how we can mathematically represent it. Now, where XK is the Capcom transmitted symbol, P is the precoder matrix. Now the received signal yk by the photodetector at the kth instant is given by equation number 1. So we have yk is equal to h is the channel, MIMO channel matrix, times f, which is the nonlinearity introduced by the LED. P is the pre-distortion over xk, which is the transmit, which is the symbol that you want to transmit. B is the DC bias, so they both combine goes through the nonlinearity, plus the external factors like thermal noise, the ambient noise, NK and this. So we generally model them as Gaussian processes, or it could be slightly different as well. So like NK is a chi-squared based distribution, which can be modeled using the Gaussian distribution. Whereas thermal noise is a relative Gaussian noise. NT is the number of, so because we're looking at a MIMO type of system, so we're looking at NT transmit LEDs and our photo detectors for detecting. And BS and B is the DC bias that is added. Now, nonlinearity, there are various ways of implementing it mathematically. One of the common functions is using lap nonlinearity. So we use lap nonlinearity by f. So xk is x tilde k is the pre-distorted xk plus the DC bias passed through the LED nonlinearity. Now this function has this following equation. VTH is the threshold cut-in of LED. Q controls the nonlinearity, so we can control the amount of nonlinearity. Very popular. This RAP model is very popular model to model the nonlinearity in the LED or even in the RF case as well. So just a mathematical model, but it can come closer to the real type of nonlinearities. So here, if xk is, let's say, less than the threshold, then the LED is not cut in, it is 0. Otherwise, if it is above the threshold, then the LED starts to operate, and the symbols get affected by the nonlinearity of the LED. Now, if you look at the impulse response for the channel between the jth LED and the ISO, it's MIMO channel as said. So H, I, J are the various elements of that matrix. So basically, I is the photo detector and J LED. It can be expressed by this equation number 3. So where alpha denotes the angle of emergence with respect to transmitter angle, beta represents the angle of incidence with respect to the received axis, P is the Lambertian, and then alpha half is a transmitter semi-angle. And if let's say you have always research in the RF world, we don't really consider these factors, but in the RF as well, when we're moving towards terahertz, these angles, they become very important. So we do consider angle of arrival, angle of departure. So, and visible light is even beyond the current terahertz bands that are being proposed to be used for communication. So here it is very important to have, because the beam is very focused. So we need to it in a way that you get the maximum energy. So angle of arrival, angle of departure, they become very important criteria as we go up in the frequency bands. Right? So now, and then there is a field of view, which is important because you have a photo detector, so it can only detect whatever comes in its field of view. And this denotes the width of the unit T. Now, some of these major contributions in this work are to look at the novel hybrid SVD based solution that is provided. We use an index to optimize the MSCR performance and approximate expressions for bit error. So we had to somehow validate our algorithms. So we have to do some analysis to find out how in theory they will perform, and then we look at simulation how good we are performing. Right. So if you look at so this is again a typical SVD decomposition, equation number 4. If you've done any course on MIMO or any research on it, you will be familiar. Even image processing, in maths, we do SVD decomposition. Similarly, because H is a channel matrix, we do SVD, so we get the vectors and values out. So we can use them for pre-coding and post-coding and the gain control. Now, pre-coder matrix is designed by P, which is lambda times P, and this is a lambda k minus 1, which is a pre-coding index at the time t. So this is something that we'll play with. Now, after subtracting DC bias and applying Bosgang theorem, yk can be rewritten as, so we had initial this yk, which was the received symbol at the signal at the receiver photodiode. Now we will reformulate it. So we so we expand this and we say, okay, alpha times u lambda k times xk plus nk, and then the other terms which are residual of this approximation for the nonlinear function fx is alpha x plus lambda, we said. So lambda h will come out and lambda p will come out for the channel and the DC bias. So combine all this, we take it as a non-Gaussian process. So alpha is uncorrelated distortion noise with zero mean and zero variance is scaling coefficient, and lambda, which is a DC bias or error in a DC bias, it is more uniform distribution. So it is not a Gaussian distribution, it is between minus epsilon and epsilon. So this makes it overall additive distortion, and within this we have to know our objective is to find out xk. So estimate xk with as a x delta k. The effective channel matrix is then found by h delta, and the condition number is given here. And the performance of the precoder is sensitive to the choice of lambda k as observed. And smaller number of lambda k reduces the condition number of the effective channel at the cost of increase in the PAPR. Hence, lambda k can be learned adaptively from received observation to trade off the condition number. Now, when we look at lambda, so lambda k is optimized using the MSCR criteria, the minimum symbol error rate criteria, where minimum of omega minus omega k. So this is the initial estimate. This is the previous one. So okay, or you can say xk is the current estimate, and xk was in the last previous estimate. We do a subtraction and in the Hilbert space, and then we try to minimize this. So it's a very common equation, but here there's a different definition for omega, and that's where the difference lies. And this gk is constraint added for QAM. So this function is there because we are looking at the minimum symbol error rate criteria. Now, because see MMSE you can apply straight away because it's the minimum mean squared error. Right. So minimum mean squared error is basically whatever you get, what you were expecting. Do a square of the error, and then you minimize it. But here we're doing a symbol error rate. So symbol error rate is dependent on the type of modulation scheme. So this function gk that we see right now, which is on tan hyperbolic function. So this is based only for the QAM constellation. So this is not the same for other type of constellations, right? So this will change. So here, because we're assuming it to be a QAM constellation, and we're designing a super quantum constellation, so my gk is this equation: tan hyperbolic beta lambda real lambda k plus 1 lambda tan hyperbolic beta lambda r lambda minus 1. So plus minus 1 we are saying these are where the symbols are expected to lie. So it's a for QAM or QPSK type of thing. But if we increase the order of QAM, again this equation will change. And similar thing we can do it in the case of our machine learning algorithms as well, where we can change the criteria based on what exact problem we're trying to solve, because by default it goes to the MSc criteria, but that's not good enough. Then yeah, we calculate the Lagrangian. So we have this minimization. We include the other terms, which is gamma, and there's this G from GK, and the Hilbert space. We try to minimize it, and then we have this update equation for lambda. So this is typically a stochastic subgradient type of equation, where you have lambda k plus 1 is lambda k minus mu, which is the step size, and then the first order derivative of the Lagrangian. The gradient of the Lagrangian can be written by this equation. Since observations compared by linearity and inner product is solved using RHS by using a feature. But basically, yeah, you can also skip that part. But interesting part is this equation number 10, what it reduces to, and the final update equation becomes this, which is slightly different than our typical LMS type of equation, right? So we had the new estimate equal to the old estimate plus this factor mu k, and then here the change occurs. Right? In case of LMS, we simply use E times X, and then we say if even X are orthogonal, then it's coming to 0. In that case, the previous and the new estimate are the same. That means the algorithm has converged. So something here the equation has changed because the cost function has changed. Now proposed order to mitigate the linearity, we use this function. We update the omega as well using stochastic gradient descent algorithm. Again, I'll skip this one. So Q is same as before for the K MSCI criteria. So kernel minimum means kernel minimum symbol error terms. This has changed. So we then in kernels, when we say kernels, we typically use a Gaussian kernel. So because it's easy to implement and analyze. So we put these kernels. So if we simply look at these KMS algorithms, we simply put these kernels on each observation. That's where the transformation happens. I think there should be some. Is there any? Okay, maybe not mentioned here, but in the paper it will be. So we simply in this criteria. So what we do is we put a kernel on the observation, and then the kernel is on the filter as well. And that's where and then once the adaptation is done, so we are doing all the adaptation on omega, right? But our focus is to get xk. Then after this transformation, we get xk back, and that's why it's called as a reproducible kernel Hilbert space, because we go into a kernel Hilbert space. Hilbert spaces are known, right? So it's a kernel because we put a kernel on top of each observation. We go there, we do the adaptation in that space, and then we come back. And then when we come back, we get the symbol, because symbol is in the Hilbert space. So there is another, if you have done a course on optimization techniques, there's one algorithm, that's a golden section search algorithm, where we do this kind of scaling we do. Or you can another equivalent or way of thinking is an example would be if you have done any implementation on a hardware where you use cube notations. So like in our fixed point maths, in our DSP process, we typically would do a fixed point arithmetic, and that's where we don't have floating points. So there's no floating point concept, but these are done using fixed point maths. So there is a concept of Q. So when we apply a Q function, Q16, Q15 based on decimal, we keep on moving. So we keep a track where the changes have occurred, and when the final solution has to be given, it has to be given in the same space. So we also temporarily move to another space. All the operations there got easier, and then we came back to the original space. So here again, the movement to RHS made these update equations easier to implement. Stochastic gradient algorithm, we did all the adaptation there. Once the algorithm has converged, we come back to the original space and give you the solution. Right? Yeah, so now there is an overtake attack, and maybe skip this part. This is the overall algorithm. I can probably also go over it quickly. There's one criteria I wanted to cover was, so this, okay, these are the results. For this, so we have a distance between two LEDs and photo detectors. We have field of view. We have this kind of scenario. So these are from standardized, values. So we use a table 3 in reference 15 that we'll see at the end. So let's say you're coming up with an algorithm, you can compare by having the same setup and then see if it is working better in certain scenarios or not. And these are various parameters that we have chosen. And we find that our results they perform better than the existing linear based ones. And theoretical and BR and our simulation give you the similar results. On the right hand side, we see a dictionary size because we have a dictionary that is built by the algorithm. If we have a dictionary size of 300, 200, what kind of bit are, how many iterations are required, and then we can also fix the dictionary size and give you an estimate what kind of bit array you will find out. So I'll skip this part. Now there's one more part I wanted to just quickly cover. This is a DFE type of structure. So I mentioned like Volterra DFE initially, right? Volterra DFE very popular in optical fiber communication. So we also applied DFE because DFE is good for ISI mitigation. So we used kernel LMS algorithm, but used DFE. Here, this is the DFE structure. This is just highlighted one, where we have a feed forward and feedback. We do a decision and then subtract the ISI. So I'll skip this part because algorithm is more or less similar, but the structure was changed. So here I'll skip this part. But again, there's a feed forward, there's a feedback, filter tabs also that needs to be updated. So I'll skip this for now. And here we are showing you results against an OpenOffice. Now this OpenOffice, again, these are given in the specification. So you can use the IEEE recommendation and use these channel models like OpenOffice with cubicles, and then benchmark your algorithm against something which is already existing in the literature. So here we see as the SNR increases, the Volterra based DFE doesn't give you much gain, but if you use the proposed ones or simply KLMS and C1, they give you better results. So without DFE, we say okay, we get some improvement, but if you use DFE structure, we get better improvement. So the red line with the circles, that's the performance, better red performance again for a KLMS DFE, the proposed algorithms. Again, a similar thing we see for the OpenOffice and OpenOffice with cubicles. Now, problem statement 3 here. I just want to look at the sparsification criteria. I think it is mentioned here. Again, for this work, you can refer to our TVT manuscript in detail for RFF page 1. So RFF gives you better criteria than KLMS. Again, this kind of structure was used. We have LED on a photo detector. So I'm going to skip this part, line of sight, non-line of sight. But I'm just looking at the sparsification criteria if it is mentioned. Yeah, on the algorithm, maybe it is not mentioned here as well. Okay. But basically what we do is in the sparsification, which you can apply in your typical machine learning algorithm as well. So when you are building a dictionary, right, in case of machine learning, even for image processing problem or other problems, you calculate the error from what is already existing. Now, one option, the best solution is you have infinite memory. So you put everything in the memory itself and then try to do comparison. But in practice, it may not be possible because again, memory is limited. So what we can do is we set up a criteria that if the error is within a certain range, we'll not update what we already have. But if it goes beyond, then we update or put this entry into this. So let's say you say error of 10 to the power minus 3. If it is around 10 to the minus 3 or below 10 to the minus 3, I will not update my memory with the new observation. But in case it goes beyond, then I will update. So that means the observations are even more different. But you see, the smaller this error is, the results in higher memory. So you have higher memory requirement. Whereas if you have a higher error, then this will transfer to higher error in your algorithms as well. So but there's a trade-off that we have to do as a practitioner, as engineers. Well, was there. But anyways, I'm coming to almost the end of the presentation. We'll open for question and answers. So if any further details you need, you can refer to some of this manuscript. Or let's say if you're interested to continue further to some joint work, then also most welcome. You can drop me email. We take a screenshot of this and maybe the next one, or you can visit our website and see what our latest system models are. Again, there's some conferences, and these are some of the key references. So El-Gala paper that I was, so they have worked a lot. So this is another work on the photonic PTL, photonic letters. In fact, our first work on Chebyshev also came in PTL. This one, this is a very classical work. As one, I think I'll still say one of the best works we have done. It comes under that criteria. Of the 200 plus papers that we have, but this is one of the good works that we have done. Chebyshev-based polynomial, very innovative. And then, there are other papers as well. So we have moved away from static type of scenario to a time varying type of scenarios. And in our latest work, in the slides yesterday, I showed that we are now looking at OTFS as a modulation scheme where we expect the user to be moving. We used in the last one we applied optical trace, so improving the performance. So there are various new models that are being explored with visible light systems as well. So there's some of the references. I'm quickly going over them. So thank you. Any questions we can take now?
Thank you, Professor Bhatia. That was a very insightful talk. So participants, if you have any questions, please feel free to ask. You can also type your questions, or you can unmute yourself and ask as well. Anyone, any questions? Okay, so if there are no more questions, then I'd like to thank Professor Bhatia. So thank you for presenting not only today, but the other day as well. I'm sure the participants have gained a lot of insights from your presentation. So if you could please share the slides, or if not the entire slide, at least a snippet of it, so that I'll be able to share it with participants, so it will be beneficial for them.
Sure. I'll do that. I have to do for the other day as well. So hopefully tomorrow I'll get some time. I'll do it. Thank you so much for having me over and organizing this FDP. That must be very tiring for your team. But it's coming to an end. So you can then relax a bit tomorrow.
Okay. Thank you, Professor Bhatia. Thank you so much.
Thank you so much. Thank you all the participants, and thank you, Professor Sandeep and your team. Thanks.
Bye. So participants, we'll have the quiz now. Anshuman, you may please take over.
Yes. Yes, so yes, we'll start quiz around 6:30. We'll share the link of online exam in WhatsApp group as well as I'll mail to register mail ID. Then you can start your quiz around 6:30. It will be start time and end time will be 7 p.m. So a couple of minutes we have. So therefore, be ready for that. Before that, just one feedback link for today's session have shared in the group. You people please submit this form as soon as possible within 6:30. Then we'll start exam.
सारे सिस्टम है
So, okay, all the participants will start online test. Hopefully, we have covered up all the sessions. Today is the last day of our MDP. So today's 3 sessions already we have completed, and now I will start exam. That exam actually will be taken place on the based on the topic have discussed last 5 days on various sessions on that particular topic. On these particular topics, the MCQ type question will be given. Total number of questions will be given 30. Each question carry 1 marks. and there is no negative marking, and the time is for the exam is 30 minutes. That means 6:30 it will start, and 7 p.m. you have to submit the form, right? Then we'll after that we'll take overall feedback, and then finally we'll validate the session entire program by our coordinator. So we'll start exam. I will share a online exam link in the WhatsApp group, and also I will mail all of you now. So then you can open the link and start exam. And exactly 7 p.m. you must have to submit, otherwise we will not consider after that, right? And this is the information to all of you. And it isn't compulsory to be appear the exam, otherwise you may not get your MDP certificate. So there is a condition there is a condition of auto site that you must have to appear exam and must have to show 20% score in the exam, and also hospital attendance. Together actually they will decide if you will be eligible for certification or not. So these are this information. Now let's move to your WhatsApp group. Check your WhatsApp group, where we'll put the exam link, and then you start your exam right now. So if you have any doubts, questions, query regarding the exam, you can ask us through this portal. It will also be an open. The platform, this platform also will be an open, and we will be here. And if you have any difficulties, questions, queries, doubt, you can ask, so we can resolve as soon as possible. Okay. These are this information. Now we'll start exam now.